Good morning, everybody. We start in the second day of the Photonic Integration Week. Today we have a session from prototypes to products. And the first speaker is Daniel Perez Lopez, co-founder and CTO for Ipronics Programmable Photonics. Please, Daniel.
Okay. Thank you, Pascual, and thank you for the invitation to this Photonic Integration Week. It's nice to see known faces around this topic, integrated photonics. Today we're going to talk about programmable photonic processors and Ipronics, the company that is commercializing them. Just to have a brief introduction, everyone in the room, I know that most of you are, of course, familiarized with the photonic integrated circuits, but it's even more mainstream electronics. We all know the performance of a CPU, of a GPU, of a field programmable gate array, and the common thing that all these devices have are that they are programmable. So one of the key features that led to the massive revolution of electronics today is actually their programmability. We are seeing that photonics, our main area of expertise, is a technology that employs light or deals with the generation, processing, and detection of light, and actually can be a very good complementary technology to electronics and some of the applications that are appearing nowadays. For example, 5G, Industry 4.0 are demanding more and more adaptability. We have demonstrated as a community that photonics in general can cope with the challenge of complement electronics wherever electronics cannot meet a certain performance. However, current photonics lack in reconfigurability and programmability, in contrast to electronics. So this talk refers to programmable photonics, the idea of being able to program light by software definition. Just as a summary, I mentioned before, we have several applications that are appearing, and some of them are present nowadays already, that are demanding this kind of flexibility. We know that electronics has been able to meet the performance so far, but for some of them, electronics is not enough anymore. And then we complement with photonics, but for you that have been working in, let's say, academic environment or even industrial environment, working with photonic integrated circuits means working with the generation of ideas, transition to a design, having the knowledge how to use the different tools to actually design your photonic integrated circuits. Once you design them, you need to cope with the process design kit of the different foundries, then wait for your slot in a multi-project wafer run, or pay a considerable amount for a dedicated run, and then deals with the packaging, the surprises that are around the packaging, a process that is, after many, many years, not yet fully standardized. And then after all these time consumption and expenses, then you will have some additional risk over all the different stages of the process. So we have been producing a technology during the last 9 years already from the lab to the market, which is programmable photonics, that deals with the generation of a reconfigurable optical processor. Is a hardware that has a software that will complement the functionality to enable its actual programmability. The first part, as I mentioned, is the hardware. It's possible to use standard silicon photonic processors, or in general integrated photonic processors, to generate these kind of circuits. What you are seeing here in the image is actually a processor, a schematic, where you can identify different programmable unit cells, defining a hexagonal pattern topology, and the interconnection of these very basic building blocks, which are tunable couplers that enables not only the splitting of the light, but also the tuning of the phase. With this very simple component, we are able to actually program the circuit. How? You can see that each building block is a Mach-Zehnder interferometer, is one of the most simple components ever in integrated photonics. And then by programming each of them, we can define, as shown in the image, different circuit topologies. We can use this to generate what you would recognize as phase shifters, waveguides, delay lines, tunable couplers, splitters, combiners, variable optical attenuators, and many others. But in order to be able to program this, we mentioned at the very beginning of the talk 3 key barriers of integrated photonics today. One of them is the knowledge required to actually design your own circuits. Secondly is the money that you need to spend on all the different processes, and the other one is the time. On average, a development of a photonic integrated circuits might take something between several months, we'll say 9 months and 18 months, approximately, depending on the circuit complexity. So if you have in mind these 3 barriers, one important is the access to the technology, the software. In order to remove this barrier from Micronics, we have created a software layer that allows most of the users that are used to program, in this case with a Python language, their photonic integrated circuit. So if you want an interconnect, it's a single line of code. If you want an optical filter, it's a single line of code. If you want a splitter, it's a single line of code. We have aggregated this hardware and the software into a rack, into a system, and we are already commercializing this huge milestone for photonics in general. The first commercially available photonic integrated circuit that can be programmed by software definition. This has been placed into a box, into a standard 19 inches rack. And then what you can get from this circuit, as mentioned, is a toolbox that allows you to program your interconnects, your switches, your optical filters by software definition. And then, just to get on the details, I would love to show you a couple of examples that you can do today with a programmable photonic processor. In this case, you can find, let's say, a conventional way to program your circuits, one by one, unit by unit. This is time consume. You will consume a lot of time. It's also risky. You might skip or have any issue, and then you need to debug. It's funny to start employing debug programming term in photonic development. Then what we can do today is with a single line of code, we are going to create an interconnect. So interconnect, our input, our output, and then we have a software layer based on mathematical models on top of the hardware and the software that allows us to find, in this case, more than 600 alternative paths in less than 1 second. You can evaluate them in terms of power consumption, in terms of crosstalk, in terms of length, and then the system will not only select the optimal one, but also program it for you. So it's really easy, and we remove, in this case, the 3 barriers that we mentioned before: the time, in less than 1 second, 600 alternatives. Also the knowledge is a single line of code instead of knowing the actual physics under an optical waveguide. If we get more and more complex, we can put these nice examples of a beam splitter. Our team has worked to get, again, from this one unit by unit programming to a single line of code programming where you can identify your input port, the selected output ports, and again, the model will find for you what is the optimal path very fast, and also program it for you based on the analytical response. It will provide a first guess. Interesting for all of you that have a lab, you might want to create a beam splitter for many different applications, either for a system, for a product development, but also for, let's say, an optical setup that you have in your facilities. In this case, you might want to have one of the outputs to be like a monitor, one of the outputs to drive the main signals. So that is also programmable. You can program the taps and then select the optical power distribution that we are sending. And why is this possible? Is because surrounding each of the ports around the mesh, we have also integrated optical photodetectors. So these photodetectors are accessible to the system and provide feedback. So it's also possible for you to create with simple Python scripts your actual programs that has feedback loops and reconfigure themselves in order to provide a certain splitting factor or to adapt in time. One of our colleagues in the team has been able to demonstrate in a couple of hours more than, well, I think each point here has several programming examples. So this is actually a statistical analysis. What we are showing here is that the possibility of programming a 1 by 1, a 1 by 2, 1 by 3, by 4, by 6, and then on and on till reaching a 1 by 26 optical beam splitter. And then we saw that the actual difference between the output ports is below 1 dB of deviation, and more importantly is that this is the first guess of the program, of the algorithm. After this, you can even run another algorithm on top of this in order to correct these small deviations. So this is only the first guess that provides the algorithm. These kind of beam splitters, beyond the academic use or the lab use, could be employed for future 5G base stations. We have been doing some measurements in the lab in the framework of final results of an ERC grant. And these examples just illustrates the case. You can transmit 5G signals employing radio over fiber techniques for distribution purposes, but also add some extra layer of flexibility, in this case, a beam splitter to direct the signal to different base stations, for example. If we grow in complexity, we have been transitioned from interconnects to beam splitters, and now can we combine more and more complexity here, in this case, an optical switch. Again, we can program this 1 by 1, but now it's not so trivial. We started with an interconnect. It was relatively easy to say, okay, this is in crossbar, state crossbar, and then the signal is going through this path. But now that we are adding more and more complexity, in this case, multiple interconnects coexisting together, sharing the same space, you start needing support. And software is here to provide that support. No? The software allows you to reconfigure the mesh in a smarter way. We have found when we were doing, for example, the previous case, the beam splitters, it's trivial to say that this kind of example was programmed by a human, in the sense that we tend to be very symmetric, and now we split 2 by 2, and then 2 by 2, and then 2 by 2, and then you get a beautiful distribution, and it's almost straightforward to say, okay, this is a 1 by 4 beam splitter. But what we have shown is that the software provides not so symmetrical or intuitive designs. And the rationale behind is that it tries to optimize, in our case, for the length. So it tends to compress the circuit topologies on a certain space. And that's really good news, because you have more space available for other applications that can be parallelized in the software. Continuing with the example, the optical switch, in this case, we are providing input and output pairs. This is going from input 0 to output 4. If we follow the path here, we will find that this is in cross state and should be doing something like this. Okay, this is the first path that we have here. And again, it's a single line of code, optical switching, and then we provide the different patterns. And this allows us to get, in this case, up to 12 by 12 optical switches. The reconfiguration time of the previous extractors and these extractors depends on the complexity. Minimum, our system currently is limited to 14 milliseconds, and maximum it takes 96 milliseconds. These are some examples that are, again, under preparation, and just for you to have a quick overview. But in this case, we are combining interconnects with beam splitters. So it's not only an optical switch. It's let's say, an arbitrary networking device that allows you to combine interconnects, switches, beam splitters, and so on, with good optical crosstalk between the different configurations. Jumping in complexity, we get onto the filters, optical filters. In this case, we have two ways of producing optical filters. We can produce them within the waveguide mesh arrangement by programming, again, each building block in order to get the different performance. What we are showing here, again, these are results to be published. We show one filter example and then the response of the other two, showing that there is a strong isolation between the circuit topologies in the mesh. And in this case, is a Match-Ender interferometer, a Ramsey filter, and an optical ring resonator. And what you have within the device is a strong possibilities to tune not only the splitting factor and then create your circuit topology, but also a very fine control of the optical phase on every single local element in the mesh. If I'm not mistaken, we are around 0.01 pi of the control of the optical phase. And that means that, for example, for a structure like this one, which is a Ramsey filter of 4 order, we could produce a phase shift in all the ring resonators that are here, one ring, and another, and we can tune the phase on these 4 structures simultaneously in order to move this filter on the frequency domain for the full free spectral range. And to finalize, we have also some customers' interest and developments, internal developments on optical matrix multiplications. This can find application beyond computing. For example, in base stations, optical matrix multiplications might be interesting for multiple input, multiple output applications. We have also a strong interest on optical signal processing in general. If you think about a DFT Fourier transformation, or even an MMI, a 3x3 MMI can be discretized or converted into an optical matrix. And then this can find application, for example, for coherent. We can convert this optical matrix multiplier into an optical hybrid for coherent detection, for example, in a programmable way. So, yeah, we have created as well the layer of algorithms that allows the users to move from a matrix definition into what is the actual configuration that produce or program this optical matrix multiplication. A quick summary of the applications that we have mentioned here could be all the technology that we have been referring to: interconnects, beam splitters, filters, switches. Everything can be applied to RF photonics in general, which is the generation, processing, and detection of RF or microwave signals employing photonic techniques. Fiber to antenna, for example, it's a nice application where you have an optical fiber and then a photonic processor on each antenna or a photonic processor on the central office in order to produce an additional layer of processing, like, for example, dispersion compensation, equalization of the optical gain profile of an EDFA. You can compensate that in order to create a flatter response and then improve the signal integrity or the capacity of the channels and so on. And we then are transitioning into pure optical applications, pure optical signal processing applications, and even computing applications, as I mentioned before, with the optical matrix multipliers, with reservoir computers embedded on these kind of programmable waveguide meshes and neuromorphic computing engines in general. And just in order to finalize, we have seen the technology per se, and the typical questions that we get from the audience are in terms of, okay, how this scales. This seems like ideal, trivial at the beginning, and then ideal, and then you realize, oh, what's going to happen with the optical crosstalk? What's going to happen with the optical loss? What's going to happen with the density, the integration densities in general? And if you study the different trends, and we have been doing that for several years, we have been relying on what's known as the Moore law in electronics that actually refer to the growth of the number of transitions that we have been able to integrate on chips. These scales doubling the number every 2 years. And we are starting to see a similar trend in photonics. In this case, the number of phase actuators, as we mentioned before, each programmable unit cell, in our case, contains 2 phase shifters. So if we measure this number of phase shifters as our optical transistor, which you can find some similarities, it's similar to a transistor. However, in our case, in photonics, we are dealing with analog signals rather than digital. And a similar trend, although now is like a lot of dots all together. But if we focus on the best 2 performers every year, we can starting to see that trend that is growing at a similar path as the Moore law in electronics. In this case, again, doubling the number every 2 years. Similar trends, different words, and then, again, the questions are around the form factor, the optical loss, the power consumption, the crosstalks, and the needs of higher performance blocks embedded on the actual system in order to increase the actual performance of the device. That's where we are putting the focus nowadays. Of course, we reach milestones on commercialization levels, but we really believe that we need to push more and more in order to narrow down the gap that nowadays you will find between application-specific photonic integrated circuits and programmable photonic solutions. Thank you. Thank you.
Thank you, Daniel. Now it's time for some questions.
Yep.
Time for some questions.
Too soon.
Thank you, Daniel. I have only one question, curiosity.
Okay.
You are working on a 50-50 wavelength right now.
Yeah.
It is possible to work also in programmable photonics in the visible range? And what advantage or disadvantage could have?
Yeah, okay, thank you. Nice question. So the question is if it's possible to transition the programmable photonic concept not only to C-band or 1550, but also to other wavelengths of interest, like, for example, in this case, visible. So in order to, I think that the answer is yes, it's possible. And then the challenges there would be, with high probability, you need to transition our current technology, silicon photonics, silicon insulator. You will need to transition to silicon nitride. And then in silicon nitride, the key 3 building blocks, well, I would say even 2 building blocks that you need for a strong programmable photonic processor are the 3 dB couplers, the MMIs that we use, or directional couplers that you can use for the programmable unit cell, the Mach-Zehnder interferometer. You really need very low loss and really good performance, as flat as possible in wavelength. And then you need a very good phase actuator. And good actuator means low form factor, means low power consumption, low crosstalk, and low loss. And then the question then would be, is there, you can find that kind of phase actuators and 3 dB couplers at that wavelength? I would say yes. I think that silicon nitride technology already, with some combination of undercuts, for example, could be potentially a technology that you can use for visible programmable photonic applications.
Thank you. Some more questions from the audience. Over there, Ruben, on your right. No, enchúfalo de abajo.
No, thank you for the presentation. Yeah, as far as I have understood, this is all the control is by thermal tuning, right? Mm-hmm. Do you have any comment, or maybe it's not my business, but on the difference between using thermal or the MEMS that now they are a thing in photonics?
Yeah, good question. So regarding the tuning mechanism that is preferable for programmable photonics, I think that this is an open discussion in the academia regarding that part. Is everyone is trying to find the best programmable unit cell that you can get in order to get this kind of circuits. I already mentioned what are the critical performance factors or KPIs that gives you the best programmable photonic devices. For me, the MEMS approach is a viable one. So far, there are no scalable demonstrators in the literature that proves that that's actually a working solution. We heard from some trials. There are European projects, several working on that, several institutions in Europe, outside Europe as well. I think MEMS has shown good performance as well on not only on programmable photonics, but also on optical switches in general. Regarding the added value or the advantage, I think that the key advantage that is claimed most of the time is the insertion loss reduction that you have for some of the programming states. But so far, in order to produce a full MEMS-based solutions, you need very accurate phase actuators. And I think that there are not in the literature lossless or low-loss phase actuators. If you really want to have an scalable programmable photonic processor today, for me, thermal optics is the only solution that allows that level of scale.
Okay, thank you. I have a couple of questions myself, despite that I know Daniel for a long time. Can you comment when you get your silicon photonics chips, probably every tuner, every coupler, everything, every interferometer is in an unknown state.
Yep.
How does your product handle that?
Very good question. So, as mentioned by Pascual, the initial state of each match sender interferometer on the wafer should be ideally cross-state. But since you may have like either design errors or fabrication errors or the waveguides, once you have a silicon photonic circuit larger than 100 micrometers, the optical phase becomes like arbitrary, random. So due to this kind of waveguide geometry defects. And so the way we have solved this is using, let's say, a smart algorithm that basically just require one single input of a laser that we integrate in our device, so it's included. And then once you specify the input, you have the algorithm running for several times, and then the system, it's self-calibrated. So basically we get the curves for each phase actuator, and that results not only in the actual mapping between the intensity or the electronic signal that you need to put and the optical power, but also gives you the optical phase deviation, and that is stored by the system.
And that can be reused many times, or you need to calibrate often?
So I always tell the story that during my PhD I was doing this not with the smart algorithm, but with one by one step process. And the story is that let's say, that lookup table that was created at that time still was working 2 years later after saving the chip on a dusty cover. So if that works, then so far we haven't seen that the calibration procedure stays on time, but the user in our case can run the calibration again and again whenever they want.
Okay, and my last, because the audience is pushing for another question. You say that your product works in 100 nanometer bandwidth. Mm-hmm. So how is that related to the couplers actually? Because
So we use edge couplers, and indeed they reach like 1.6 wavelengths. I think 1.62 until 1.5, and even lower than that. So the actual limitation is not coming from the edge couplers from the chip to the fiber, are coming from the 3 dB couplers that we use in our... I
was referring to those.
Okay. So to the programmable unit cell. So yeah, that's one of the key performance that we are improving and improving every day, which is the actual bandwidth of the 3 dB couplers. And that's actually, it's limited by the application. Some of the applications can tolerate, that is then converted to the extinction rate of your match senders, can tolerate 30 dB, others 25, others 20, so that gives you margin for...
Okay, thank you. There's one question over there.
Thank you very much. I just wanted to know, because you're a fabless company, right?
Yep.
Then I was wondering, I'm not going to ask you where do you fabricate your chips.
Thank you.
But what I'm going to ask is, how robust is this design to transfer it to another foundry? In case you have problems with the current, can you transfer this to another foundry, or you have detected that there are issues with when you move on?
It's a good question. So I think that the core technology that we have developed is pretty standard for this product version at least. So it will be easily transferable to different foundries. We have done this design on our early days based on E-beam platforms, then transition to more commercial foundries. Very similar designs in, I would say, 4 different foundries already. Each one based on a different process, but the actual concept holds from foundry to foundry. I think that it's pretty standard, and that allows us to transition from different foundries. But of course, working with the same foundries years and years allows you to fine-tune some of the components and to squeeze the performance to the next level. And then moving to other foundries means starting again some of those processes.
Okay, thank you. Maybe one last very fast question, if not. Yes.
Just very quick question. Which is then the power consumption of an individual phase shifter in the state-of-the-art device that you have? Only the phase shifter, I mean.
1.3 milliwatts per pi. That's the one that we have in the standard one. And I think that our, let's say, ballpark is moving around. Our target is getting below 5 milliwatts for other optimal designs that we have been working on in parallel to the standard one that we integrate in the product.
Okay, so thank you, Daniel, again.
Yep.
Then we move to the next speaker, which is my colleague, partner, fellow and friend, Íñigo Artundo, CEO for VLC Photonics.
Thank you, Pascual, and thank you for inviting me once more to Photonic Integration Week. So, hello everyone, I'm Íñigo from VLC Photonics, and I'll be discussing a little bit of the challenges when we work with many customers in photonic integration, and what are the challenges that they are facing moving from prototyping to production. So, but quick introduction for those of you who don't know VLC Photonics. So we are a company spin-off from the Technical University of Valencia here 12 years ago, mainly focusing on offering development services, mostly engineering services for design and test of photonic circuits. As I said, the company was founded back in 2011, 12 years ago, but it's only in 2020 that we became part of the Hitachi group. And nowadays our team is located still in the campus with the laboratories that you have probably visited yesterday, and we have a team of 20 people, most of us engineers, half of the engineering team with a PhD, so it's a very high-level, well-educated team. A little bit about Hitachi High-Tech. So it's a large corporation based all over the world with divisions, as you can see, mainly headquartered in Japan, but with offices in Europe and in the US as well, with 3 main divisions working on biological and medical instrumentation for analytics, also for semiconductor equipment, mainly etching tools and microscopy tools and scanning electron microscopes. But we actually hang from the Industrial Solutions Group, which is a division that provides services to industries that are developing products. In our case, we support on the optical communications department and in general optical modules department. Okay. So this department actually provides all kinds of components, mainly from Japanese providers. As you can see here, they work with all the major transceiver manufacturers of the world for mostly telecom and datacom transceivers, and they provide all the components that are embedded into these transceivers. So, okay, quick introduction about photonic integration. Probably this is the Photonic Integration Week, so you all know this. Photonic integration is about getting a complete optical system, or as much as you can of an optical system, into a photonic circuit. And it's following the same evolution path as in electronics. And the reasons for this is that mainly, obviously, you reduce the volume and weight, which in some cases is a very practical advantage. We have seen yesterday the presentation of DAS photonics. So for defense and aerospace, avionics, this is very critical. Also for having handheld devices as well. Of course, it simplifies very much the assembly and packaging. You don't have many discrete optical components, but only one single chip to stabilize. And this gives you much better mechanical and thermal stability. For example, in applications like automotive, LiDAR, this is very critical. And what I think is most important, and I believe Ipronic's presentation now has clearly shown this, is that it enables you to scale up the complexity of your optical systems. So being able to think of optical architectures and optical systems that you wouldn't be able to think otherwise if you don't integrate them on a chip, because you have tens, hundreds, even thousands of components on a circuit. And of course, like in any semiconductor technology, this allows you to scale up in production and address markets that include like millions of units, tens of millions of units. We have seen also the presentation yesterday by Rockley Photonics, embedding some photonic circuits in a consumer wearable. You wouldn't be able to do that in the order of millions of units if it wouldn't be for semiconductor technology, and eventually also reducing the cost. So this technology has been growing and developing for the last decades. It was originally proposed at the end of the 60s, beginning of the 70s, and since around 2005, 2006, we started to see this technology applied to telecom devices, a bit earlier than that actually. Started with very basic PLC technology based on silica devices, but it quickly evolved into more complex silicon photonics technology, mostly supporting telecom devices, coherent telecommunications and fiber-to-the-home devices and things like that. Around 2016, Intel released also their own transceivers for data center applications based on silicon photonics, and that started a boom on the market by using silicon photonics as well for this transceiver in datacom, not only in telecom, but datacom, so probably like one order of magnitude larger volumes. And what we see now is that the trend is moving also to applications that are one order of magnitude bigger than datacom, which is computing and also sensing. So this is the shift that we are seeing in the last years. So this is being enabled mostly by a new business model in photonics, which is the fabless business model. Originally, all the photonic component companies were vertically integrated, so having all the development process in-house, like from the design to fabrication, testing, and packaging. And the fabless model, which is an existing business model in electronics, enables you to decouple all these different processes at different stages to different partners. So you may keep, for example, the definition of the system in-house, but you may be able to externalize the design to a design house, the fabrication to a foundry, and the testing and packaging to an OSAT. Okay? So this same evolution has been happening in photonics in the last years. In the beginning of the 90s or 2000, most of the companies developing optical components were fully vertically integrated. And it's more or less around the year 2000 when we started to see some commercial tools for photonic modeling, not something that companies developed in-house, but actually software companies providing these systems. And the basic silica technology, PLC technology, was starting to mature, mostly for doing splitters, array waveguide gratings, things like that. It was in 2005 then when we saw the emergence, mostly in Europe, of generic foundries. By generic foundries, I mean having a generic process that many customers can use for different applications. By the birth of EpixNet with EpixFab and Jepix, mostly European foundries like IMEC, Sealeti, TUI in Eindhoven, etc. More or less around 2010, we were born, so the first photonic design houses were emerging. Also, the foundries started to have the first version of their photonic PDKs, process design kits. So this enabled also next step in the design processes. And it's in around 2015, 5 years later, that what we could say the big EDA players like Cadence, Mentor, now Siemens, or Synopsys started to get seriously into the photonic software landscape. Also, some industrial foundries like Tower, like global foundries like AMF, like GCS, they started also to get into the photonic integration market as well. And also the market itself started to take up. So in terms of volumes of shipments, in terms of revenue, etc. And what we see in the last years and what we see the emerging trend now is that in the design side, we see a lot of IP cores and optical engines being now commercialized by different companies. The need of optoelectronic co-design, so for specific applications where you need to co-integrate the very high-speed electronics with your photonics. Also, we start to see the emergence of new materials beyond the basic ones that traditionally has been proposed in the industry, like silicon photonics, silicon nitride, indium phosphide. So we start to see now polymers, lithium niobate, barium titanate. And of course, the foundries are able to provide more mature PDKs and in order to scale up the volumes. So we have been working with all these foundries and technology platforms over the years. We have been supporting these processes, development, and component libraries for the PDKs over the years. We have worked in silicon nitride, as many of you know, with the CNM in Barcelona. Also, we have been involved in the European PICs for Life platform pilot line with the foundries of IMEC and Lyonics, and also supporting Ligentech also on their development of their component libraries. On the indium phosphide side, we have also been collaborating for many years, also with a the second largest foundry in indium phosphide in the world, which is GCS in California, and we have developed the TABI platform, which is a regrowth-free platform where you can develop photonic integrated circuits with different functionalities in a fully industrial platform capability of 20 to 30,000 wafers a year. Also here in Europe, we have been supporting the Impulse JEPIX pilot line, collaborating with European foundries like Smart Photonics, the Fraunhofer HHI Institute, and 35 Labs in France. But this has been more focusing on the design and fabrication side. But there is a big elephant on this room, okay, which is the photonic backend. Much has been discussed on this, on the importance of photonic packaging, but I would say it's not only the packaging, it's on the die and wafer level characterization to support the process development, component library, and PDK development. It's of course on the assembly and packaging, but it's also on the testing, functional and reliability testing of the packaged device. And that is what in electronics is known as the backend, right? So, of course, many companies struggle in the decision of should we build that backend in-house or should we outsource that, like in electronics? Because, of course, building that, it's a significant investment. In terms of infrastructure, you need clearly clean room space, you need probing stations, you need very high-end instrumentation. Of course, you need many consumables, and of course, all this needs to be redundant because obviously, if you are in production, it needs to be 24/7 in operations. Beyond that, of course, beyond this infrastructure and equipment, you also need the investment in personnel. You need well-educated and trained engineers and technicians that have skills not only in photonics, but also in things like automation, in software, for big data processing and analysis. And of course, you need everything around that, like quality certifications, calibrations. So this is a significant investment as well here. And of course, in terms of timing, this is a critical decision to make. Do you want to develop that in-house, which may take a few years, or would you like to have, in terms of product development, a faster timing? And this is not only the procuring of all these instruments and the hiring of all these people and training of all these people, but also installing it and configuring it to the highest performance. So let's see a little bit what this entails. In terms of characterization, we are talking here about first visual inspection of the chips or the wafers that are being fabricated, the metrology that usually is being done at the fab side, and also the optoelectronic characterization of the devices, components, or circuits. This is very important, starting from the foundry metrology, because this gives you also first identification of the issues on the wafers and the epitaxy on these wafers. This is more complex in 3-5 materials, maybe simpler in silicon or silicon nitride, but still it's very substantial work. Of course, you need to evaluate all the tolerances on the lithography and etching processes and then further deposits. And with this, you extract the fab yield, which is the yield mostly on the process control monitoring cells and also on the PDK blocks that some foundries start to monitor now. But also on the application side, at the customer side, you need to validate, first of all, the fab process, because you need to make sure that the foundry did their work. You also need to be able to validate the building blocks that eventually you have been designing yourself, not the ones on the PDK, and also, of course, the circuit that you have designed. And this will give you the application yield, which is different from the fab yield. So this is important to emphasize. And of course, if there is something that has gone wrong, you need to do the failure analysis, and if everything has gone well, then you need to feedback all this information into your compact models. For that, we have been developing extensive capabilities at VLC Photonics over the last years. We have a couple of clean rooms, as you have seen yesterday, where we have different, first of all, visual inspection tools for chips and wafers. And then we also have different die-level testing setups, semi-automated, still mostly manual work, and then all the instrumentation around that to be able to characterize these chips, both at 1550 or 1310, which are the typical telecom and datacom wavelengths, but also in the visible wavelengths, and now we are starting to work on the mid-infrared as well. In terms of electrical testing, of course, we have all the equipment required for voltage and current sources, but also RF systems in order to reach 110 gigahertz, which is a very unique equipment here in Europe. From Keysight, specifically this light wave component analyzer, being able to reach 110 gigahertz, for example, for measuring very last generation modulators in new technologies like lithium niobate, polymers, or things like that. But of course, this is what you have seen. This is mostly for die-level testing. And if you want to scale up your product from prototyping to production, well, in the beginning, you can start with multi-project wafers or shuttle runs where you have a few dies, a few tens of dies maybe, and manual bare die testing is good enough for this. But in the moment you move up into the prototyping or engineering stages, then you start to have several tens, several hundreds, in some cases thousands of dies to be tested, or maybe a few wafers if you go into a dedicated run. So in this case, you really need to have some automation embedded. And of course, once you move into pilot production and full production, full automation is needed. And in this case, you really need to move to wafer level testing. This gives you different advantages. Of course, it accelerates product development. It supports the sorting of binning of non-good dies for packaging purposes later on. Supports clearly failure analysis because you have much more statistical information on the devices. And also this statistical information feeds back the design models. So that's also something that we have been working on. We have 2 full wafer level testers. Actually, you saw one yesterday on the UPV Fab clean room. The second one just arrived yesterday, so it's still unloaded from the truck. So actually, these tools, these wafer level testing tools, have a visual inspection system that allows not only for doing visual inspection on the chips or the wafers, but also to recognize all the fiducials for the probe alignment. It's a thermally controlled chuck, so it can accommodate not only small wafers, 3-4 inch wafers of indium phosphide up to 12-inch silicon photonics wafers. And it also has the capability to do bare die testing with a special chuck adaptation that we have built at VLC. It has different probing arms, both for optical and electrical testing. The optical ones can work with single fibers or fiber arrays, specialty fibers as needed as well. We have been embedding, for example, even laser periscopes as well, not only fibers, but also other optical coupling structures, and with very quick alignment and probing time. And also, in the electrical side, we are also able to do not only DC testing, but also RF testing as well, wafer level. Also, very importantly, all the data collected from this wafer level testing needs to be also processed and analyzed and collected into a database, which is also something that we have developed as well, all the software required for that. And not only that, but also all the instrumentation setup, the probing recipes and the test executives can all be put into a package and be transferred to a larger OSAT or a customer premises for scaling up the production. So just to give you an idea of what kind of things can be done when you start to do wafer level testing, some examples of projects that we have done in the past, being able to measure tens of hundreds of measurements in thousands of structures, both wafer level and die level. As you can see here, well, this is just back of the envelope calculations, okay? This is very rough figures. But just for you to understand what kind of timings are we talking about, for probing times, we are probably well below 4 seconds, but let's assume 4 seconds. And if the measurement time for a trace acquisition of a few hundreds of nanometers or tens of nanometers, a spectral sweep with a tunable laser, and around 50K number of measurements, that can easily quickly scale up to several days. So you have to be very conscious when you designing your test plan, when you move from prototyping to production, because testing can quickly scale up in time. So no matter how quick your probing is, how fast your tunable laser is, timing can be skyrocketing quickly. So of course, having fast instrumentation is very much needed. Also, this is very good for yield analysis. In this way, you are able to evaluate what are the yield distribution along the wafer, or along different wafers, or different lots, or different batches. And this is very important information for the foundries when you are doing process development. And it also gives you a way to evaluate also the sensitivity to different design parameters. So here, for example, we evaluated different test structures in different reticles, and you are able to see what is the sensitivity of certain parameters of the fabrication process or on the design based on the testing information. Of course, this also gives you much more visibility on the repeatability of the measurements, which is something very hard to get when you do die-level testing on a manual way. It's not only because of the alignment tolerances or the probing tolerances when you do manual alignment, but also, for example, the thermal stability over time. If you are able to do very quick measurement acquisition, then you minimize the influence of thermal variations that you may have as well, for example. Also, one important thing, once you have done the characterization, is to be able to test these into some breadboards. So we have been developing also some basic test assemblies to simplify or ease the characterization of these chips. This by no means is a full package, but this greatly simplifies on the engineering. So we are able to do, for example, the design of some basic PCB carriers or ceramic carriers, and then bond these chips, photonic chips, from different materials into these carriers for DC or even RF operations. We are also able to do the fiber pigtailing to connect optical fibers and take these chips out of the laboratory, and all the required connectorization of the chip into the carrier using wire bonding or flip chip techniques, but also on the connectorization of the carrier into some external connectors and the thermal management as well with thermistors and peltiers. So what this gives you is a very portable and low-cost assembly that you can take out of the lab to be tested, maybe in the field, and it gives you also very quick turnaround time with stock parts that we have at VLC. And we also partner with different packaging companies to scale up these kind of approaches into full-blown packages. So a little bit more on the packaging side, because no matter how much time I have to say this, it's always a surprise when it comes. Packaging can be very expensive. And I'm not talking only about R&D and prototyping, but also if you move into production. This can be easily 60% of the cost. So it's very critical to have these packaging considerations from the start in mind. So design or lay out your chips for manufacturability, but also for testing and packaging purposes. There are many different differences among packagers. So in terms of the capabilities they have for die processing, different timings they have, volumes, costs possible, the pigtailing capabilities, the DC electrical connection capabilities they have. And one more important thing that we are seeing now is also the transition to hybrid assemblies. So, for example, the co-integration of different chiplets into a carrier or different photonic chips into the same package. Not every packager is able to do that, or together with micro-optics as well. And of course, very important, once you have the package device, then you need to be able to do the component reliability in terms of thermal stability, vibration, shock, radiation, depending on the application and market. Some of these will be more important than others, and eventually be able to certify that. So that's all. I just want to give you a couple of takeaways, because I think this is very key. I think it's clear that photonic integration technology and also the markets that it's serving are coming of age now. But we see there is a lot of investment being poured into the field. Of course, competition is growing in all the different aspects. So there are plenty of optical engine vendors for every application you may think of. And these optical engine players are investing more than 2 million, up to 20 million euros in developing products that can take 3 to 5 years product development time. Of course, here photonic FPGAs can help, but in many cases, all these people are developing photonic ASICs. So anyone moving from prototyping to production needs to be aware of the market and the technology, the status of the technology and the competition in the market. And there are challenges ahead when moving to industrializing a product. and ramping up in volume. So nowadays we have mature processes and component libraries, but these are required to enable more complex and validated chips. And of course, a scalable photonic backend is really needed. So for all those needs, please contact us because we can support you here. And we are also hiring, so feel free to join our team as well. Thanks a lot.
Thank you, Inigo, for the talk. So, time for some questions. Yes, Ruben, please, over there.
Hi, first, congratulations for the talk. My question is about the automatic testing wafer system. So I think you have to use grating couplers, no, in order to measure the kind of wafers. And the second question is in case that you have different wafers for different customers, different configurations in the wafers, how adaptable is the testing system? You have to change the head, or you can use the same head, or how do you manage that, that question?
Good questions. So typically, indeed, the optical probing has been done using vertical grating couplers in silicon photonics. So this means coming with optical fibers from the top of the wafer. Problem is that in many cases, in silicon photonics, people are moving to edge coupling due to bandwidth restrictions of vertical grating couplers and losses. So you actually need to test edge coupling. And also in other material platforms like silicon nitride or indium phosphide, you also need to do edge coupling. So what we have done over the last 2 years is to develop a process to also enable to do edge coupling at the wafer level. So by doing some trenches on the wafer, that you can actually use V-grooves as well for that, you are able to embed some kind of optical periscope into the trench or into the V-groove and be able to access the waveguides from the side. So edge coupling can also be done at wafer level. And regarding the second question, that's a good question because usually these probers are very expensive. So usually they are only sold in a specific configuration towards production. But in many cases, when customers are doing engineering towards product development, you need a flexible tool. You need some flexibility that allows you to change wafer sizes, configuration of the probe arms, because nowadays we have 2 optical probe arms, left and right, and we have 2 electrical probe arms, north and south. So sometimes depending on the chip configuration or the layout configuration, if we have designed that chip, we can adapt the layout according to our configuration, but sometimes we test chips from other people that have done the designs themselves, and they have not respected the specific rules. So our tool is actually flexible enough to change the configuration of these probing arms in the way we need. So for example, we can have like 3 electrical probing arms and 1 optical, or only 1 optical, or 2 optical only, or 1 electrical and 1 optical. So this can be fully configured, yes.
Okay, thank you. More questions? Yes, over there. Espera.
It's very nice what you are doing. In the case of the edge coupling or band coupling, I wonder if you are testing it, what about, for example, in the vertical, there's no problem, or less problem about reflections and fabric perot and this kind of thing, but probing edge coupling, how do you deal with these kind of problems?
Mm-hmm. That's a very good question. So this is usually not a problem in silicon photonics or or silicon nitride because these are passive technologies. But in the moment you hybridly integrate silicon photonics or silicon nitride with 3.5s, or you actually do that in indium phosphide, then indeed you may have reflections because then you have a trench which is behaving as a cavity, and then you have like Fabry-Perot effects. So by doing that, there are 2 ways to approach these. So either you have waveguides at an angle, so you minimize reflections. Of course, it's not perfect, but it's usually good enough for testing purposes. And the second thing is to do wafer level coating, which some people are starting to do now as well, in indium phosphide. Yes.
Thank you.
Oh, sorry.
Thank you, Inigo, for the nice talk. Inigo, you have indicated that the packaging cost is still, even for scaling up, production, it is 60%. And I think this is still a very big problem facing the integrated photonic community, because we tend to focus on the cost of the chips, but I think if we really want to go into the market, because for a lot of applications, such as sensing, we have as a competitor with electronics, electrical sensors, and things like that. So if you look at the budget breakdown of this 60%, what is really the biggest hurdle, the biggest chunk of cost in this 60%, and how can be reduced further?
Yeah, that's a difficult question, Sami. I hope characterization cost can be decreased over time. As processes get mature and component libraries get mature, I hope that characterization cost can be decreased. Packaging and testing, it really depends on the application, because for some applications, packaging can become really complex. I'm talking about, like, for example, chiplet packaging into custom assemblies for co-packaged optics. Like, this can be really complex, while for some other applications, even like we work with some customers that are doing all optical processing on a photonic chip, but there is no optical input or output to the, to the outside world. So in this case, the packaging is relatively simple because you can use electronic means for that, no need of optical fibers. And reliability also depends very much on the market. Some companies are working like Das Photonics for aerospace, so you can imagine the reliability requirements you have in there, or aerospace, medical, avionics, even automotive. In automotive, even the foundries need to be qualified for working in automotive. So I think this very much depends on the application. I cannot give rough numbers here.
Okay, I think we need to move to the next speaker, so let's thank Íñigo again.
So third speaker is Jonas
Lewerman from BioHero.
Thank you very much for the invitation to give this presentation on this conference. So yes, I'm Jonas Lewerman. I'm from the company BioHero, a photonic sensing company. And with this talk, I want to answer three more or less simple questions. Who is actually BioHero? What are our objectives, and what is our sensing approach? But first, let me present myself a little bit. I'm actually not from Spain, actually, where I'm participating in the founding of BioHero, but I studied in Germany, electrical engineering, then came to Malaga in the Photonics and the F group from the University of Malaga, and then founded or co-founded BioHero in 2021, and currently in the position of the head of engineering. So BioHero was founded by three different groups from the University of Malaga, which is the Photonics and RF Laboratory from Professor Íñigo Molina. And then we have the Laboratorio de Dendrímeros Biomiméticos y Fotónica. I didn't get the English translation. From Professor Ezequiel Pérez Enestrosa, which is a biochemistry group. And then we have the Allergic Diseases Research Lab from Professor Maria José Torres, which is one of the leading experts worldwide for drug allergy detection. So with the help of the investors Bullnet Capital and the Invierte de Ceriti, we received a funding of around 3 million euros. So BioHero is a deep tech company and is currently applying very sensitive integrated biosensor technology in a very international and multidisciplinary environment. So we started in October 2021 with 1 employee and more or less 50 square meters office and lab space. And currently, more or less 100 years after the founding, we have a team of around 10 employees and 2 interns with different backgrounds in engineering, software, chemistry, and of course administrative stuff. And the idea is to grow to more or less stable size of around 12 to 16 employees in the next 2 years. So, to answer the objective of Bioherent, maybe I have to explain the application, which is drug allergy detection. So, the problem nowadays with drug allergy detection is that typically when you enter, for example, a hospital and the doctor wants to prescribe you a certain drug, for example, penicillin, and typically what he does, he takes your file history and looks up for some keywords, and he finds some comment about, okay, he received this drug and had some kind of reaction to it, then you're typically classified as allergic to this drug. So, but typically in 70 to 90% of these cases, that's a false positive. And that implies a very high cost for the healthcare system, because then the patient has to receive alternative antibiotics. And the problem here is that nowadays methods are not sufficient enough for the detection. The gold standard for allergy detection in general is the Immunocap from Thermo Fisher Scientific, which is a quantitative in vitro method, but only has a medium specificity and medium sensitivity. That means you have a lot of false positives and false negatives. So there's also another method which is more laboratory work, which would be the basophil activation test, which has a quite good specificity, but the sensitivity is not good enough. So the only test which is reliable is the drug provocation test, where you inject the drug directly into the system of the patient. And that's associated with a high risk for the patient, and because he could have anaphylactic shock or some other side effects. And that is why you have to perform this test in a very controlled environment, where you have doctors around which can act appropriately if something happens. And of course, this is associated with a high cost for the healthcare system. So our objective is to develop an in vitro medical diagnostic device based on integrated photonics with high sensitivity, high specificity, label-free, with short immunoassay times, and in a very, let's say, easy-to-use plug-and-play solution with single-use tests for a laboratory instrument and or for the point of care. So probably all of you know how integrated photonics biosensing works, but let me shortly make a summary of the functionality. So typically you have your silicon wafer on which you grow your silicon dioxide layer, and on which you have your silicon, in our case, silicon nitride waveguides. And this waveguide is exposed to the environment, so it's not buried in the silicon dioxide. So within this waveguide, you have a mode propagating, and after propagating a certain length, you have a certain phase shift, which typically is constant when nothing changes. And this mode has an evanescence field tail, which is penetrating the water surrounding it. So if there's any refraction index change within this evanescence field tail, this will alter the propagation speed of the mode, and then you have a certain phase shift after propagating the length of the waveguide. So this is a refractive index sensor. To make this sensor a biosensor, you have to add a biorecognition layer. So you do this, for example, by functionalizing a certain antibody on top of the surface, and then you inject the antigen, and if the antigen binds to the surface, then you alter the refractive index close to the surface, and this will introduce phase change. Of course, you cannot detect the phase of the light directly, so you have to introduce a reading architecture. For example, one very popular eye reading architecture is the ring resonator, where you apply a certain wavelength range, and then you read the transmission spectrum of this ring. And if the light meets the resonance condition, you get the certain dips in the transmission spectrum. And if you introduce here the antigen, to the ring resonator, you change the resonance condition, and then you can correlate the phase or the wavelength, the resonance shift change to the amount of antigens bound to the surface. Okay, this is a technology which is already applied by Genelite, which is the first integrated photonic biosensing company worldwide. But there are also other reading architectures, for example, the typical Mersenne interferometer with direct detection, where you typically split the light into the reference waveguide and sensing waveguide, where the reference waveguide is buried in the silicon dioxide and the sensing waveguide is exposed to the water or the buffer medium or the analyte. And when the light recombines, for example, by Y-splitter or 1x2 MMI, then you receive a signal which is moving in the IQ plane only on the real part, with a dependency to the cosine of the phase shift between sensing and reference waveguide. So the problem with this technology or with this approach is that you have problems with sensitivity fading and signal ambiguity. So signal fading is when you are in the interferometer diagram at, for example, 0, pi, and 2 pi, where when you have small changes in the phase, you will not see any change in the amplitude. And then you also have directional ambiguity, so you actually never know in which direction the phase is moving. So typically, what is done is to apply some kind of modulation to this technology so that you can circumvent this problems of sensitivity fading and directional ambiguity. So what we do is we use a Mersenne with coherent detection scheme. So we, instead of recombining it by a 1x2 MMI, we use a 3x3 MMI and split the incoming signals from sensing and reference waveguide to the 3 different outputs, which are 120 degree phase shifted to each other. And from those 3 signals, we can make a linear transformation to the complex interferometric signal, which transfers into a circle from which we can read the phase change with constant sensitivity and without signal ambiguousness. So if we change the phase in one direction, then the point on the circle will move in one direction, and if we go back, then the point will move in the other direction, and we don't have any problems with sensitivity loss and ambiguousness. So just a small recap about the advantages and disadvantages about resonant interferometric structures or sensing architectures. Typically, resonance structures require high-quality light sources, which you can scan over a wide wavelength range, or you need a spectrum analyzer. So that's very costly. There are also interferometric types of sensors which also use the spectral content of the sensor, which also typically require more costly equipment. Then you have also the direct detection approach, where you typically need medium quality light sources. And then for the coherent detection scheme, you can actually use very low quality light sources, so you don't have to invest much money into a very high quality light source. For example, for our experiments, we bought a handheld fiber test laser from Amazon for around 30 to 40 euros, and we got quite good results. So to verify the performance of a biosensor, typically what you do is you inject different concentrations of sodium chloride to introduce a certain homogeneous refractive index change to the sensor, and then the smallest amount of refractive index change you can detect, that's more or less the detection limit. So resonance structures typically receive a detection limit from 10 to the power of -5 to 10 to the power of -6 refractive index units. Interferometric, direct detection interferometric structures around 10 to the power of -6 to 10 to the power of -7. And with the interferometric approach I did in my thesis, we got down to 10 to the power of -8 to 10 to the power of -9 refractive index units. So another performance test you typically do is you functionalize your sensor with a certain type of protein, for example, a certain antibody, and then you inject the counterpart, and then you try to make the same experiment as with the bulk sensing. So what we did here is we used the C-reactive protein, which we wanted to detect, so we functionalized the antibody of the C-reactive protein to the surface, and then injected different concentrations, increasing concentrations of the C-reactive protein to the sensor in an additive immunoassay. And we did this with the 2 different light sources, where we received with the limit of detection of around 180 picograms per milliliters with the external cavity laser, and then we used the Fabry-Perot laser and received more or less a detection limit of 1,700 picograms per milliliter, which is a factor of 10 between them, which is not that big considering the spectral contents of the different light sources. Unfortunately, I cannot give any current results we are doing in our experiments because we are still in the development process. So I cannot comment anything about what we are currently, let's say, doing in our experiments or in our development. But maybe one thing I would like to mention is that we are considering a new approach in the Korean detection scheme, where we want to use bimodal sensing. Just to make a short summary of bimodal sensing, where I'm showing 2 different figures from a photonics group here from Valencia, which did a very nice work here, and also from Laura Lechuga, of course, for bimodal sensing, where you can see here on the left side the direct detection approach with the reference and sensing waveguide separated. So only one of those arms is actually exposed to the environment or to the solution you are injecting. The difference here, the bimodal sensing waveguide, is that you use the same waveguide to make the sensing. So the reference mode is also affected by the injection. And the actual sensing content is the phase difference between those modes, which you later extract. And you can do this, for example, with the vertical waveguides, where you have 2 modes in the vertical direction, or you do this in the horizontal direction with 2 different modes. So what we want to do is, let's say, a dual polarization or bimodal coherent detection, where you have still 2 different waveguides, but on each waveguide you have 2 modes. It could be, for example, TE, TM, or T0, TE1, or TM, T0, TM0, TM1. So what you then do is you split both paths by a polarization or mode splitter, and then for each mode you make a different coherent detection scheme. So with this coherent detection you can actually do layer discrimination on the surface of the sensor, and you can also compensate different effects from baseline drifts by temperature or from other drifts causes. So that's more or less the presentation. So thank you very much for your attention. And if there are any questions, I'm happy to answer.
Okay, thank you, Jonas. You surprised me. Finished like 4 minutes earlier than I expected. Thank you very much. So now there is time for questions.
Hi, Jonas. Alvaro here. So I wanted to ask you about the competence that you have now. So you have instruments already in the market from Genelite. How do you scale in specs and cost with respect to these options?
With Genelite as an example?
Yeah.
Okay. So Genelite is using the ring resonators, and they have let's say, a very big instrument. So it's more used for the laboratory. What we try to do is develop a technology which can be directly carried to the patient. And this is important because for the application, for drug early detection, you don't have that much time. So right now, when you do the drug provocation test, this requires a lot of time, is very expensive, and would be much more efficient if you had an instrument which you could use directly the patient side. And do the testing there within some minutes. You have the results, allergic or not allergic, and you can give the prescription. So we save a lot of time and a lot of costs. With the instrument from Genelight, you cannot do this. You cannot transfer the big instrument to the patient side directly. So this is more an instrument which is used in a separate laboratory where you have to bring the sample to.
Hi, great talk. I was wondering, within your business model, are you guys plan to do this functionalization yourself, or you plan to subcontract, or do you plan to just offer kind of like the Photonic platform so anyone can functionalize whatever the heck they want?
So right now, the business model includes that we do at least the development of the functionalization, and then maybe when we go to the product phase, then outsource this functionalization. But in principle, yes, you could also use the Photonic platform and give it directly to the user and say, okay, you can do the functionalization if you want to.
Okay, thank you. Any other question?
Hello, nice to meet you. My question is regarding the dual polarization device. How are you going to ensure that the polarized light that you need is entering into the transceiver with that specific polarization?
You mean on the
bimodal transceiver?
You mean the detection side?
I think it was like the two last slides, I think. Yeah, that one. So you put that you specifically want T0 and T1 entering the last waveguide, and TA and TM entering the first one. And I was thinking,
it's in both cases it would be the same. This is just the example. So TE, TM would enter the sensing waveguide and also in the reference waveguide. I just wanted to show you could use TE, TM for both, or TE0, TE1 for both.
Oh, okay. Thank you very much then.
Yeah.
Okay, thank you, Jonas. If there is no other question from the audience, I may have one. Can you comment a little bit on the practical side of the story? So how are you going to build an instrument? Because the photonics part is a tiny part of the instrument. Yeah. And then how are you going to solve practical things like, changing a cartridge and coupling light, which is probably one of the nightmares that the many groups that have addressed this topic have found.
So there are many opportunities, let's say it in this way. The photonic side, or this photonic design of the chip or fabrication, is actually the smallest of our problems, because the photonics is working. So yet the problem is actually working the packaging, bringing everything together, because you have the different concepts of the functionalization, which is a very, very, very big issue. To make this reproducible, so the functionalization of the waveguides, so that you have high specificity and high sensitivity from the chemical point of view. Then you also have the problem from the microfluidics, which is also a big challenge to make an instrument which is in, let's say, a plug-and-play solution. So you have where you enter the cartridge into the instrument. You have directly a good microfluidic connection. You have also an optical connection to the device without any problems. The functionalization, so you have many concepts which are a big challenge, and we are currently working on solving different problems which are occurring. So we are still in the developing and proof of concept of this technology.
Okay, thank you. Any other question? If not, let's thank Jonas again.
So the closing talk for the first session today is by Ligentech, Mariam Amer, please.
Thank you. Thank you very much for the invite, Pascual. So yeah, I'm Mariam Amer. I'm heading the design and layout team at Ligentech. Okay. And yeah, the talk today will mainly address the challenges and the future from prototyping to high volumes. So what about Ligentech? Well, we are based in Lausanne at the EPFL campus, and we are a foundry for low-loss silicon nitride integrated photonics. We have a European distributed team with four locations, with headquarters being in Lausanne. We also have an office in the Paris region and people working from Spain and Belgium. However, our chips have a global reach, going from the far east to the far west, but we also cover many countries also in Asia. So why integration, photonics integration? We have already answered to this question, but a nice example is quantum computing, and this picture that I'm showing here is from a lab in China with bulk optics for quantum computing, and if you compare that with a chip where you can have integrated all these beam splitters, all these fibers, mirrors, alignment stage, you get not only a scalability, but also a very rigid system that you don't have to do all this readjustment. So photonic integration is a scalable solution for applications that are not scalable with discrete optics. So yeah, silicon nitride is our material of choice, our base platform, and one of the main differences from silicon photonics is that you would cover a wavelength range going from 400 nanometers up to 2.3 microns. And yeah, it's clear that there will be markets that we will share, of course, with silicon photonics, but then there are more applications out there where silicon photonics are a bit more difficult or just impossible to access, just like biosensing, spectroscopy, or quantum computing. So our main offering is a very high quality LPCVD silicon nitride, where the light is confined in the core, giving access to very low propagation losses, small chip size, dispersion engineering, and very high power possibilities going from visible to infrared. So how we see it as a combination of silicon nitride with this very low loss performance and high power possibilities with silicon photonics, where we have this small size chip and also the tools available in the CMOS lines to scale it up. At the end, what we deliver are photonic integrated circuits that are ready to be packaged. Our platform consists of different nitride thicknesses. Our base platform is the 800 nanometer silicon nitride, but we have also developed other thicknesses like the 150 nanometer silicon nitride that may go more to our visible application, or because of whatever reason you need to enlarge your mode, then you can use this 150 or something in between and still having low loss performance below 10 dB per meter. Then to these different silicon nitride thicknesses, we add heaters modules for thermo-optical tuning. We also provide the possibility for multi-layer stack of this silicon nitride that you can use like an optical bridge or like on a highway when you want to propagate different signals in different heights of the chip. But we also developed the RIB module and what we call the local cladding opening for sensing application or for heterogeneous integration. This platform comes with an extensive PDK where we have design rules, layout technology files, building blocks, IP cores, and all the passive components that you may have in the bulk optics that the designer can use as a Lego block to build the circuit. So all these building blocks start from different kinds of waveguides. We have delay lines, crossings, ring resonators, polarization beam splitters, polarization rotators, and very important for us that we consider is the optical I/O to have a very low loss coupling to an SMF fiber or different kind of fibers. This PDK is built in different software houses that provide you from the design level component to layout up to circuit simulations. So here we show how if you make use of this information available in the PDK, you can get your first design working right first time. This is under a collaboration with ANSYS numerical R&D team. We requested a crossing working for TE polarization, mainly optimized for TE polarization at 1550 with a compact footprint. And as it can be seen here, there is almost a perfect match from the simulated figure of merits expected from simulations to the measured ones. And in this case, it was above 26 fields on 3 different wafers. Then here, we also have a building block, which is a 1x2 MMI, acting as 3 dB splitter, developed with our colleagues from VLC Photonics. You do like your nominal design, then you have your corner analysis, or we really recommend to have the corner analysis to take into consideration the process variation, so you know that your device will still perform as you expect. Then we go to fabrication, and in this case, these wafers were measured internally by our wafer level tester. And just if you use properly the PDK information, you have this reliable design, this reliable process. And here what we show is that over 6 wafers, these measured MMI excess losses, more than the 90% of the cells were in the expected range from the simulations, and more than the 95% of the cells show the designed splitting ratio with a deviation from the ideal value of below 0.2%. So yeah, making use properly of this PDK, you can really have your design working properly and first time. Then technology and offering for LigentTech. So our technology and offering is that we cover everything from early R&D up to manufacturing with a seamless journey from the ideas to volume. So we have a fast prototyping with the established technology, fixed layer stack that we offer through MPW runs. Indeed, today is the last day for design submissions, but in 1st May, we have already the next run registration starting. So if they are accessible in our website, but if you are interested, don't hesitate to reach out to us, and we will provide all the information. But yeah, then we also have some custom runs, design and layout support, characterization capabilities, and packaging support. But then there are also projects where we have to adapt this layer stack, and this is in a custom PIC development, or even to go beyond what is available now to get into the R&D, and this is what we offer in LigentTech Lab, where we offer an early access to materials that we are studying or to layers that we are not standard yet. And once this has been proven to be working, this process or these new layers have been proven to be successful, then we have the capabilities to go to pilot and volume fabrication in a high-capacity wafer fab with a fully automated testing and in automated quality system environment. But yes, being a perfect platform for passive optical functions, there are limitations when active optical functions are required, and this includes light source, light speed modulation, or detection. So we believe that with a high application diversity, we need to take the best from the best. So we see like the silicon nitride as the basic platform for the general circuitry, where we have this comprehensive PDK, very good low losses optical I/O, and that we have also the capabilities to scale it up to volume, and then to integrate the active part with the best material per application in this base platform. There are several technologies to do this integration, and for example, we show here the monolithic integration, heterogeneous integration, and the hybrid one. And the difference from the left to the right is that the left one is the most advantage for high volumes, but it's true that there is a limited material of choice. Then we have the heterogeneous one in the middle that you take advantage from wafer technology, so you can bond from one wafer to the other. You have the best material for your application. It has a low loss potential, and you can try out emerging technologies. And then on the right side, we have the hybrid integration. That is a way that we use for quick turnaround. For example, putting an SOA or a laser or a photodiode, but coupled to silicon nitride chip to get prototyping out to be tested. So here I would like just to show a few examples that we have. In this case, we have an indium phosphide chip, but coupled to silicon nitride. As it said in this slide, it requires a flat and smooth chip facet. So that by using our technology, in this case, you can have the chips that are ready to be but coupled to an SMF fiber or co-packaged with an indium phosphide chip, as in this case. So as it's shown, we have this fiber array, which is but coupled to the silicon nitride chip. And by using this module, which is internally and externally called as XPOT, we are able to enlarge our mode to almost 10 microns, MFG. So the impact of that is that, okay, when you have only one fiber, you can play a bit more to have this good alignment of your fiber to your input. But when you have a fiber array unit, already the provider gives some tolerances of the accuracy of the fiber placement in the order of hundreds of nanometers. And by using these modules that we have, the coupling efficiency from this SMF fiber to the chip will not be impacted by this misalignment or this inaccuracy in the fiber array units. An example of the heterogeneous integration is wafer-level bonding from lithium niobate to a silicon nitride or a chiplet 1 to silicon nitride. Where how we see it is that we have the silicon nitride acting as the passive part. You have all your circuitry there. Then by using an escalator, you can translate your mode into the lithium niobate layer. You do your modulation there, taking benefits of the material that you are interested in. And then you go back to the silicon nitride, where we have the low propagation losses and all the benefits that I mentioned and I will still mention during the talk. So yeah, now what I would like to discuss are a few application examples, and we will start with external cavity diode lasers. So here we show to enable narrow line with laser implementation in the in this side of the silicon nitride chip, we have an anti-reflective coating and a size converter. Then we also have some phase shifter with metallization to be able to accurately and stably shift or tune the resonances. And this has been already published by a few groups, but in this case, what we want to show is that thanks to the low propagation losses and the Vernier filter effect, you can get line width of the laser below 3 kilohertz, with a power level of tens of milliwatts, with very good signal to noise ratio, and with a tuning range in this case of almost 60 nanometers. Then the other application field is communication, and here what I would like to show is an AWG design. That it's already known that they are very sensitive to losses because they accumulate phase errors, but they are also very sensitive to temperature, and here silicon nitride has much temperature stability if we compare it with silicon. But not only that, is that it's a scalable solution again, and due to the confinement of the mode, you can have a small footprint for your AWG. Here is an image extracted from this publication for a Gaussian AWG fabricated in the wavelength range of 1 micron. And it can be seen that we have crosstalk values below 35 dBs, insertion losses below 0.5 dBs, and the accuracy of the peak wavelength standard deviation is around 0.5 nanometers. Then the next application is LiDAR, that we believe will play a key role for autonomous driving. And in the field of LiDAR, wide-angle area coverage available today mainly relies on mechanical components moving to allow us to scanning, but this has some limitations, and it will limit the scan rates, it will reduce the reliability, and it will imply high costs. And here we believe that silicon photonics or silicon nitride photonics will will give some solutions to these limitations. So, yeah, but again, in LiDAR we have an additional key requirement, and it's that we need a lot of power on the chip that needs to get out, and then you collect the reflection with few photons. And here silicon nitride has the advantage that it doesn't have 2 photon absorption like silicon has. So you can put a lot of power in your waveguide, and indeed we have tested up to 10 watts power in our waveguides. Another approach to do LiDAR is phase arrays, and one sophisticated approach is that you use, instead of having one single input and grating coupler plane where to do your beam streaming, you can use multiple inputs with multiple lasers, so your coverage area is much, much larger. Here we have the experimental output of this design that were published by our colleague, Pasquale, and his group. And yeah, we show that with multiple input star coupler for 2-dimensional optical phase array in a compact design, it's something that will be a good alternative for this beam steering and LiDAR application. And switching to the next application that is getting now a lot of attention lately is quantum computing. So in quantum computing, every photon counts. You want to have a very low loss circuitry. You don't want to have movable parts. So if we take a look again to the image I showed at the beginning, if you can have all these mirrors, all these fibers, all these beam splitters in a single chip, that you get not only this phase stability, but you get also a rigid system where everything is integrated in that chip, but also you can scale it to volume. So with the semiconductor manufacturing techniques that we have, we are able to scale it and to process the same chip several times, and to have it up to 1 million devices per chip. Yeah, and one chip that we fabricated at Ligentech and that was published by a company located in Canada, Xanadu. This chip has silicon nitride circuitry. It consists mainly of a pump distribution for the laser distribution. Then we have here high Q resonators to generate the Q bits that they have. Then we have the filtering, where they filter out these squeezed states that are generated at different frequencies. And then we have the interferometer part, which is the computing part, where all these generated Q states are interfering in between them. One key metric again here is propagation losses, or quality factor of these ring resonators. And because the generation rates of these states scales with the cube of the Q factor. So again, propagation losses are key for really quantum computing. This service, indeed, just a comment, is available through the cloud. So you can do we can say that you can do some computations and run some operations on a device fabricated at Ligentech. Okay, so I think there were a lot of information. To sum up, we have a very low loss platform technology, reaching down to 3 dB per meter. We have an extensive PDK with all kinds of passive components. We are working now in the active part. We understand this particular optical I/O as key, where we offer here, again, coupling losses to a standard SMF fiber below 1 dB. We also offer MPWs, as I said, and dedicated runs with very short turnaround time. We have also a flexible R&D line and the capabilities to scale and transfer the process to volume lines to fabricate on 200 millimeter wafers. That's all from my side. We are also hiring Inigo, so there we have the openings, and you can also check them in our website. Thank you very much for your attention.
Thank you. There's already one question on the back side.
Amadeo.
No, I want to congratulate you for the talk and for the impressive work that you are carrying on, because it's really nice to see. And just my question is about the wafers, because the the set configuration of the wafer is not so standard. So my question is, the wafers are fabricated, integrated by you, or you buy commercial wafers with this silicon nitride configuration?
We buy the masks, but the wafers, we are a foundry, so we provide the silicon nitride. We have the IP of these processes, so yeah.
Yeah, but the wafers are commercial wafers.
Yes.
You buy. Okay.
You have the 100 millimeter one, 200 millimeter one, but yeah, they are commercial wafers from providers.
And the other question is the lithography method that you are using?
Stepper.
Stepper, okay.
Over there.
Thank you very much. Very interesting. And well, we are looking forward to work with you. And one of the questions that I have, you show lithium niobate on silicon nitride. And my question is, do you grow the silicon? Do you deposit silicon nitride on top? Or how do you... The lithium niobate, sorry.
No, we have this module, for example, the local that I mentioned, where we have this local opening, where you can put your lithium niobate chiplet or...
Okay, it's a hybrid integration.
Exactly. So you have only in the active part that you need, you have this lithium niobate, and then the rest of the circuitry is in the silicon nitride.
Okay. And in terms of the alignment of the waveguides from lithium niobate to silicon nitride, do you have an idea of what are the losses, insertion loss?
It's a good question. As I said, it's not available now for production, and here we make a really clear difference in between what we provide as production and what is in the R&D stage. This is in an R&D project that we are developing. It's ongoing. So once we prove that it's something that we can provide to the customers, we also open the doors to customers that want to join R&D projects to develop these materials or these interests. More than welcome.
The chiplets that you have is from other Swiss provider? Thank you.
Don't answer that question. Okay, any other question? Yes.
Can you please give us numbers about the quality factor for entangled photon generation and the propagation losses of the waveguides for the other part of the manipulation of the circuit?
Yeah. So ring resonators, we have measured. What we promise is that we have 2 million Q factor. We measure it. We were able even to measure above 20 millions, but this is what we guarantee, but it exists. And about propagation losses, for example, let's say 1.1 for this AN800 silicon nitride, 1.1 micron, you can have 0.07 dBs per centimeter, but we were able to measure for other waveguides that are not, that are a bit wider, but not a highway. We have measured below 3 dBs per meter. Not only one time, but in several lots, in several runs, we are able to measure this level.
So good. Thank you very much.
You're welcome.
Hello. Thank you for the presentation. I have a question about the quantum is a topic very important. You need this kind of waveguide for quantum. And have you tried what happened in your losses in your platform when you go cryogenic temperature, or you don't try this?
No, our main field is not to do this application. This comes from the customer application side, but we are able to do this support based on what they need.
But do you have any feeling if I go cryogenic, maybe the wafer broke, or what happened?
Till now, we don't have these problems from my best knowledge, but I cannot tell you just a closed answer in this sense.
Okay, thank you.
Welcome.
One on the back side. Boyo.
Thank you very much, Mariam, for this nice presentation. I have a doubt about your waveguides. Okay. You have presented several thicknesses. Okay, you have this 800 nanometer thickness, 400, and as far as I remember, 150 nanometers. Okay, for the 800 nanometer thickness and 1 micron of width, is it monomode TE00?
It's slightly, let's say, slightly multimode. It starts to be multimode, but the behavior is still as it was, as it if were a monomode one. You don't have to care if you go with 1 micron about, unless you have a specific application that you really need to have only TE, for example, then it may. Design related.
Sorry. I mean, yeah, for the 400 nanometer thick, which is your width of?
I mean, for to be in the single mode,
yeah.
Depends on for which band you are targeting. Because
yeah, well, at 1550, TE00.
I don't know it by heart. I'm sorry. But it's quite easy to do the design and the study for the NFX to extract
Thank you very much.
Welcome.
Okay, Jad is assuming you have the mode solver embedded in your brain.
Hello. Is there a way to access your PDK? Do you sell it or rent it or whatever?
No, the PDK, I mean, it's accessible, of course, under a DKLA agreement. If you are interested in joining an MPW, it's offered in the same pricing of the MPW cost that you may be interested in. So yeah, it's accessible.
Okay, I think that we have plenty of questions, so unless anyone else wants to talk, we are closing the session now. Thanks, Marian, and all the speakers again.
Thank you.
So just before we go into coffee, I would kindly ask the speakers of the next session to come by and load the presentation. The rest of you are free to go for coffee. Thank you.
Hello, good morning. Hello again to everyone. So let's continue with this fifth session of the Photonic Integration Week. This session is dedicated to new startups in photonics, and we will start this session with our colleague Guillermo Carpintero from LeapWave Technologies. So, Guillermo, when you feel ready.
Okay. Okay, thank you very much for the invitation. Actually, what I'm going to show you is the startup, which actually was born here, I could say, because last year in this same event, we met our investors and made this LeapWave deep tech spin-off possible. It comes from the research in my group at the UC3M within a European project, TerraMeasure. It's a future and emerging technologies project. And actually, we've developed a new technology that I want to show you today. And when we realized we created 3 patents out of it, we just submitted the 4th. And when we thought about exploiting it, that's something that is impossible within the university. So we've taken the step, and thanks to the science law in Spain, that has eased things. And what I'm going to talk to you is how the solutions that we've created are going to pave the road towards 6G, in which you are already listening about terahertz frequencies. Frequencies that are in the range from 300 gigahertz to 3 terahertz. 3,000 gigahertz, which is a bit scary, but I'm going to show you that we can help. I don't have an outline because I just want to keep the surprise of through the whole presentation. So basically what I'm going to show you is, I just told you about 6G, and actually 6G, I just gathered some recent developments and basically, show in the Mobile World Conference, you can actually see already that key companies are already stepping into this frequency range. From Keysight Technologies, and what you see here, hope this is the laser, yeah. From Keysight Technologies, a key instrumentation company, basically they use some extension heads, which are made in the US. Rodesbarts, a European company, also has extension heads. All is based on very specific electronic technology. And basically, this is the Ericsson microwave outlook, pointing out that currently the E-band 60 to 90, this was already included in 5G, is picking up. The growth rate is 500%, and right now is 6% of the links that are actually installed. Mainly in Germany, because in Spain it's so easy to put fiber that the wireless is used somewhere else. But already frequencies in the D-band, the D-band is, the motto right now is that the D-band is the new E-band. Basically because now all the efforts are being put in the E-band, and what you can see is that already, even at higher frequencies, there are developments. So now you can say, okay, but you are in a photonic integration forum, so why this? Because photonics is actually a key technology to reach this high frequency range. This is from Professor Tadao Nagatsuma in Osaka University, and he has been tracking all the developments for achieving 100 gigabit per second on the air, links of 100 gigabits per second speeds. And you can actually see that even 250, this is actually his work, Professor Nagatsuma's work, at 250, this is reached by photonic technologies. This is enabling us to transmit high data rates, and basically it's using this high frequency carrier. That's because that's where bandwidth is available. We are talking about the bandwidth of 44 gigahertz.
So you cannot think, I want to achieve this in the 2.4 gigahertz range, because there is no space. You will crash into zero. You have to move to higher frequencies, and that's the millimeter and the terahertz wave range. And there are different competing technologies. Electronics, I showed you before, that's the current mainstream in the technology, using Schottky multipliers, resonant tunneling diode technologies. The other key technology is photonics. The advantage that photonics has, that the electronics doesn't have, is we are tunable. We've seen the tunable lasers, and they cover, we are talking about nanometer tuning ranges. That's hundreds of gigahertz. That's what we need. In photonics, it's easy, because basically we are working at 193 terahertz. So a few terahertz is easy. If you talk about this percentage bandwidth, it's nothing. The problem with the photonic technology is basically the amount of power that we can deliver. And that's something that we are addressing. But it's a matter of power. And the problem is not to lose that power. Once you create it, the problem is not to lose it. And then there are other more fancy technologies like quantum cascade. These are set apart because these usually require cryogenic cooling at these frequencies. So basically, what the two challenges that have been identified is that we need new ICs. Photonics is there. Actually, photonic ICs is what we've been developing. And also, what is needed is not to lose the power that you generate. And that's in the packaging. So, as I told you, this is our lifetime project, this integrated microwave photonics. And this is something we did in 2014. We, together with 3.5 Lab in a project that I coordinated several years ago. We've shown many times this picture because it's the first monolithically integrated transmitter that reached up to 150 gigahertz from 5 gigahertz. That was the tuning range that we had in this. But we actually saw we had thermal crosstalk, other issues. Actually, in one wafer to put all these different components monolithically required compromises. It was difficult. So we move on to hybrid integration technology. After we did this landmark, it was followed by UCSB, and we've moved together with Fraunhofer in their polymer platform. We've moved to the same optical heterodyne on chip, and now we are also working on hybrid integration with Lyonics. You can actually see the performances that we achieve, narrow line width, and very broad tuning range. Continuous. This is a continuous tuning range. Still, this was done through a series of European projects. The last one of them is Teraway. And sort of this path is easy. We have the RF frequency on the fiber. Losses are the losses on the fiber. So that's fine. Which is the problem? Well, the problem is at this end, where we have the antenna. Because the antenna, if you want to put it on chip, it's already a problem. And if you want to put it, and if you don't put it on the chip because it's on the top of a mast, then it's a bigger problem. Because this is what we learned when we packaged this device that I just showed you. We did this, and then we had to deal with the RF interfaces. For the input signal, this is where we introduce the data at high speed. If you have 44 gigahertz of bandwidth, you want to use it. So you have to think big in these interfaces. But okay, that's doable. But then the output, that's at 100 gigahertz or beyond. That's where the millimeters and the terahertz waves are. And what you see here is the photodiode in the chip, launched in a microstrip line, a coplanar waveguide, then a launcher into the rectangular waveguide, because that's the standard way you connect things at high frequencies. And what is the problem of both of these interfaces? Actually, each one has its own. Okay. For the RF, if you want to put RF on the chip or drive the signals from the connector in the package to the chip, you usually use planar RF waveguides, and those are very nice because you don't have any dispersion, so you can use the full bandwidth. But the problem is that they have very high losses, extremely high, especially if you compare. It's 3 orders of magnitude that of fiber. So you actually have a problem here because if you use these coplanar contact pads, you know you are going to hit a very hard wall, and you are going to start losing the power that has been hardly achieved. If you move to the rectangular waveguide, which is the standard interface for high frequencies, because the coaxial interfaces that are commonly used as well to get the signals out of the chip and connect is the fiber of RF, the coaxial cable. It ends at 110, and now with hero effort up to 20 with a 0.6 connector. 0.6 connector is not even standard yet. The 1 millimeter connector, it is a standard, but it reaches 110. Pushing it a little to a limit, Keysight has pushed this to 145. But then, beyond that, you have to rely on rectangular waveguide standards. And this means these are, you have a limited bandwidth. So we are developing broad components in photonics, and then when we package them, we are restricted to narrow bandwidths. So electronics wins again. What is the advantage if you are not going to be able to use it? So these are things that really bother us, especially because one important detail is how do I measure my devices on these frequencies. Okay, I use a VNA, so fine. Your VNA, if you use a baseband unit, you reach up to 70, maybe. If you want to reach higher, then you have to use extension heads. We have these extension heads up to 110. And if you want to go further and you want to go into rectangular waveguide, then you have to use extension heads. These are the ones that I showed you before in the setups, in the demonstrations done by Keysight and Rodesbars. And these cover limited bandwidth because the rectangular waveguide is limiting the bandwidth, is restricting the operational bandwidth of these components. Each one of them is about 60K, and you have to buy a couple because you need the transmitter and the receiver. So you are talking about the 100K investment per frequency band. So we look at our budget, and we said, that's not affordable. If it's not affordable by us, it will not be affordable by many other people that would like to make savings here. But this is not the only problem, because still, you see, we are in these extension heads, and you still need to reach a chip. So you actually need probing tips. And these probing tips, of course, you have them with coaxial up to 110, and you have them with rectangular interface up to 500. And the higher the frequency, this is one thing we all know. The higher the frequency, the smaller the feature size, so you shrink in size. So us, that we are aiming to 6G, we are saying, you are reducing the size, your antennas will be smaller, you can hide your antennas in the furniture, you will be invisible networks. And it's like, yes, but the smaller you have to touch your component to measure it. And the size of the separation of the tips, this is the separation, it's not the size of the tips, is 150 micron, which is twice the human hair thickness, twice the diameter of human hair. So you can think, okay, is that fragile? You bet. It is extremely fragile. It's not something you can put, you give your PhD students, say, okay, do a landing. And I always had a joke of, it was a practical joke of going to the RF conferences and ask the people in Form Factor or other manufacturers of tips, and can you do a landing? It's like, okay, just because it's you. It's very fragile. So you have this landing problem. You have to land the tips on the chip, and it's basically like land on the moon. If those of my age, you probably have played this moon lander, and you know that you always had to go through different iterations and they always crash because you always landed on tilt or you were too speed. That's what happens. And you basically broke the tips because you have to land them. This is the extension heads that I showed you before. You have to connect the rectangular waveguide because this is the lowest losses, and then you have the tip, and you have to land this on the chip. And it's like, okay, lunar is moon, rocket lander again. No, we did the training years ago, but it's really expensive because those tips, and those tips only work for the frequency range that the rectangular waveguide operates within. So it's expenditure that is CapEx, is a capital expenditure that you have to do for each and every frequency. So if this is one of the mottos is, if you don't like it, change it. Okay, easier said than done. But fortunately, we had a European project to fund us doing this development. And this is what we came up with. We came up with a new concept. Basically, we told the guys from Anritsu that show up in my office, why don't you use wireless? They said, wireless? How? It's like not touching the substrate to make the contact. It's use evanescent coupling. Again, easier said than done, but we've done it. We are using near field contact. This is very important because if basically why we are doing photonic integration is saving cost. I demonstrated you that we are doing this because we are saving you from the buying so many rectangular waveguide twins, because basically they are the same thing with different package. And we want to be compact. And if you want to be compact, you need to work on the near field. And what we have, actually these are probes. We maintain the same concept that the electronics uses today. Is if you are used to approach your probe to the substrate, we will do the same thing. We don't want to change, we don't want to make an optical system because that's not going to be accepted. So we are doing a proximity approach, but we don't have to touch. And actually, this is the design, this is the probe. We, of course, have a low cutoff frequency. This is by design, and we can erase this, but right now we are not worried in the low frequency, we are worried on the high frequency and the bandwidth. And what I'm showing you is that from 50 gigahertz, that's by design, we are reaching up to 350 gigahertz, continuous. So no more rectangular waveguides. And now it's where we can actually use the advantage of photonics to generate these frequencies continuously. And we have a launching system for the RF to make this contact. And this is what we measure, up to 110 because that's the AVNA that we have. And what I'm showing here is, this is our probe with the cutoff frequency, the low cutoff frequency that I showed you before, okay? But basically, the trend of the frequency response is the same as the 1 millimeter connector that we have here. So the losses that you see here is not because of our contact, it's because of the W1 connector that we are using to feed the dielectric waveguide. So we are using this dielectric waveguide to basically make the contact. And it can be used for probing, and it can be used chip-to-chip contacts, using the same structure. And I think I still have some minutes of time. Well, I'm going to then end up the slides, and then I'll show you a video if I have the time. We actually demonstrated that these dielectric waveguides allow for the data transmission. We were not happy with just a sine wave. Sine wave is easy. You just have one tone. You have to send a data stream. And we use actually 16-bit QAM signals through the signal. And what we saw is that back-to-back, and back-to-back is connecting the photodiode and the Schottky diode together. And this is blue is with the electric waveguide. Same thing. You can say it's not the same. I see that they are not overlapping. Like, yes, but you see, this was manual alignment. So we did it within the means that we have right now. And then what do we do with this? This is the technology we developed. And what we did is, together with the funding from Bundnet that we found here last year, we started a company. This is the team that lives at the edge of photonics and the edge of electronics. We are living in the terahertz gap to fill it and bridge it with our silicon, the electric waveguide structures. We have, actually, this is the, it's not on purpose, but this is the electronics experts and the photonics experts. This is the two edges, and we have our electronic designer. It's a small team, but actually is the best team I could think. That's why I started this as well. It's I found these besters, but that was not enough. And most important part, and this is always I've tried to convince my university in the process, the most important part, most valuable, is this team. And the company is basically bringing, typeset speed, change of letters type is bringing the speed of photonics into the electronics, but basically is bridging these two technologies. And because basically one thing, we are LeapWave, because basically we are not talking about electronics or photonics, we are talking about waves. It's what unites these two extremes. And I just wanted to show you a video. Okay. I'll try. Wait. I have all the presentation. I don't want to mess this. Because this is, I think this is all preloaded. Okay. Okay, yes.
This one, right?
That one. Okay, right. So basically what you see here, this is our 110 gigahertz VNA. This is the extension heads. This is where we have connected the electric waveguide with W1 connectors to the extension heads. And what we have here is the height. So you are seeing here live the height at which the probe stands from the DUT. And we are making connection. Actually, you will see that this will lift. So we see 100. This, I think the voice, I should have canceled the voice, but anyway. This is 100 microns. And at this point, you actually see that we made the connection. And we have this 130 micron distance that we can stay from. And when we reach, you see, around 50, basically we don't have any further improvement. That's the tolerance of our positioning. And we have tens of microns tolerance in all directions, in C, in Y, X. So it's fairly tolerant to misalignment of the probe into the landing pads. And this is it. Thank you very much. You're welcome.
Okay. Thank you very much,
A great pleasure to.
From the audience?
Thank you for the talk, Guillermo. I would like to know about the photodiodes.
Yeah.
You didn't mention them, or only one photograph, no? It was external.
Yeah. No, I didn't. I didn't mention the photodiodes because. But that's a good point, because part of the project and one of the patents has been in the development of a new type of photodiodes, in which I didn't mention it, but the material that the chips are made of has a high refractive index. So basically, if you look at it, it's basically like a resonator. For RF, it's a resonator. It's a Fabry-Perot, and it influences your measurements. And actually, the probe tips that I show you, the GSG tips used in RF, as you go higher in frequency, just how the landing is made excites substrate modes, and you have high losses. It's one of the biggest problems that the industry has in this point. So we need to excite. I also show you that we cannot excite with W1. And what we've done is to develop a new type of photodiodes to connect to the dielectric waveguides, to launch the signals, and be the it's an optoelectronic probe. It's a photonic generation of the RF, and it's launched on the dielectric waveguide. Then you can use it over the broad bandwidth. And for the photodiode, we actually had to develop a new type of photodiode in which it's not just an optical device. It's an optoelectronic device, and it's not just optical converter. It has an optical waveguide to feed the optical signal into the photodiode, and then it becomes an RF waveguide. The semiconductor is an RF waveguide to guide the signal towards the electric waveguide. So we don't have any, we don't have losses. I didn't show that because that's, I just had 30 minutes.
And the bandwidth of this photodiode? Or?
In theory, it's well, not in theory. In practice, the photodiodes have a 3 terahertz bandwidth because these are terahertz spectroscopy photodiodes. I didn't show the partners in the consortium, but we did this in collaboration with Fraunhofer HHI. And what we told them is, we love your photodiodes, but we don't like the silicon lens. For spectroscopy is fine if you are doing free space, but we're not interested in free space. We're interested in waveguide integrated. And for that, the photodiodes are not good enough. We want to change it. And they said, okay. So we designed a new type of photodiode structure, and we are currently measuring the power that we can generate up to 3 terahertz. Because at 3 terahertz is where the signal hits the noise floor in spectroscopy. So we are still to demonstrate what is the bandwidth of these photodiodes. We are crossing our fingers to increase over the 3 terahertz, because that's the limit of the project. So we want to deliver what we promise.
Thank you.
Any other question from the audience? If not, then let's thank Guillermo again, and then we will move to the next speaker. Well, now it's time for Sonia García Blanco, and she will present Aluvia, the next spin-off company.
Thank you very much for inviting me to be here today presenting Aluvia. Aluvia Photonics is a very early stage startup that is a spin-off from my group from the University of Twente. And we are trying to commercialize the aluminum oxide photonic integration platform. So in this presentation, I'm going to introduce to you Aluvia Photonics first. And then I'm going to try to give an overview about the aluminum oxide platform and try to explain what are the advantages of this technology. I will first talk about the operation of these waveguides in the ultraviolet, and then in different wavelength bands. And one very important thing is that we can dope the material with rare earth ions, and then we can also provide optical amplification. And then I will conclude. As you know, all here, yeah, we're in a big conference. If you want to go from the, this is the laser, Yeah, if you want to go from a kind of system, optical system like the one in the left, and make it scalable, then you need to go to photonic integration technology. And then you gain, of course, energy efficiency, increase speed, reduce size, reduce cost, scalability, as we have heard in many of the presentations before, and also novel functionalities that you may not be able to do if you are working in this kind of system. And indeed, as you all know, of course, integrated photonics is the backbone technology in many applications, such as the ones that I put some photos here, you know, the AR, VR, the data centers, autonomous driving, etc., etc. And there are three main established photonic integrated circuit technologies, such as the indium phosphide, silicon, and silicon nitride, that can provide very nice performance for operation from around 400, 450 nanometers up to the mid-infrared. However, there are other applications that can also find a lot of benefits from miniaturization thanks to photonic integration. For example, quantum, UV Raman spectroscopy, UV-Vis spectroscopy, etc., etc. However, these applications find it a bit difficult because at the moment there is not a commercial platform that can operate at these wavelength ranges. And in my group at the University of Twente, we have been working in the aluminum oxide platform for the last 10 years. And the advantage of this technology is that it has a very broad bandgap, so that it can extend the operation window down to around 200 nanometers. So that will enable operation and miniaturization of systems in the ultraviolet wavelengths. However, the technology does not only work in this frequency range, of course. It can also work in the visible and up to the mid-infrared, up to 5 micrometers or so. Therefore, for applications where you want to operate both in the ultraviolet but also in the visible or in the near-infrared, it could be very convenient to just use one platform, the aluminum oxide platform. And that's how we got very excited, and we decided to try to commercialize this technology as Aluvia. And here I explain a little bit how we formed the name, so aluminum oxide, so AL. UV applications, because this is kind of the niche that we want to exploit first. So UV and via waveguide via, but also way towards the future because we think we can enable new emerging applications. So how do we want to position Aluvia? So what we're going to offer is just foundry services of peaks in the aluminum oxide platform. So yeah, you have heard about this business model many times already during these weeks. So basically, we want to receive designs and fabricate the peaks. And we believe that thanks to that, we're going to enable new markets in the ultraviolet wavelength region. And here I show some of the performance of the waveguides. In this photo, we see a propagation in a slab waveguide at 377 nanometers with around 0.5 dB per centimeter of propagation loss. Here we can see a channel waveguide, fully edged channel waveguide, that is like a spiral, at 4 or 5 nanometers with around 1.5 dB per centimeter loss. And here is a realization of a near UV tunable laser operating at 400 nanometers. And I will explain all these in the following slides when I get a bit deeper into the technology. So what is our value proposition? Pure play foundry, so we want to fabricate peaks because that's what we like doing. And yes, these peaks will enable applications, broadband applications from the UV till the mid-infrared. And we are working towards the development also of a PDK, of basic building blocks to ease the transition between idea to fabricated peak. And one thing that we find is very important is that we would like to strive to a fast turnaround. So really, like a couple of months delivery for the peaks, fabricated peaks. And at the moment, we're setting up everything, of course, and we're working mainly in 3 demonstrators via an EIC transition project that we received and started in December. So I will show later the integrated tunable UV lasers because we have results already from there. But we're also developing a quantum ion trap device and also some devices for UV Raman spectroscopy. we had a study, okay, I just want to give you an idea of the applications that we think our technology can enable to see if you feel identified with any of them, and then, of course, feel free to contact me. So, of course, the UV Raman spectroscopy that we are starting, UV-Vis spectroscopy that also should extend into the UV, white light sources that can extend down to, yes, 200 nanometers, tunable lasers in different frequency ranges. Oh. Just 1 second. Okay. Ion traps, AR light engines, because of course the performance in the blue of our technology has lower losses than other platforms because it's at the edge where the silicon nitride can still perform nicely. So then it could have advantages there. And structured UV microscopy. We do the manufacturing at the moment at the Mesa Plus Nano Lab, which is a clean room facility attached to the University of Twente. And there we have a 1,250 square meter class 10,000 clean room with 1,000 square meter of specialized equipment that permit us to do from the position of the layers, lithography, etching, cladding, heaters, the whole process flow. And we are situated in Enschede in the Netherlands, and I want to show you a little bit the ecosystem, peak ecosystem in the area. So this is the campus of the university, and we are here. But next door in the gallery building, this is a startup incubator. We have Lionics International, and we have Quix, the quantum company that does quantum peaks. And Fix is here a little bit further in the high-tech factory. And then in the technology park, which is here, we have also a design company, Synopsys, well, a software design company, Synopsys. Okay, so I introduced you a little bit to Alluvia. And now I would like to get a little bit, give you more details about the capabilities of the platform. So we started with the UV operation. So we did some experiment to try to figure out the transmission window of the material. And for that, we have a UV-Vis spectrometer. And we put a sample. It was a quartz sample with a 1 micrometer thick spattered aluminum oxide layer deposited on it. And in the other branch, we just put the quartz substrate. And we measure the transmission. And here is the transmission loss in dBs. And you can see that it's more or less flat down to around 250 nanometers, and then it starts slowly going up. So at least until 250 nanometers, we should have, good transmission. Then we deposit a slab waveguide. I already showed quickly this photo before. So this is our wafer. We're working in 4-inch wafers. And this is in a Metricon equipment, which is a Prisma coupler. So we couple the mode of the waveguide. It's a 700 nanometers thick layer that is monomode at this wavelength. And the laser that we're coupling is at 377 nanometers of wavelength. And there is a fiber attachment that it can see the decay of the light along the strike, and we measure 0.5 dB per centimeter on the as deposited layers. We're also developing a CMP process to further reduce these propagation losses. Then we did our e-beam lithography, etching, and cladding deposition. And we use a cut-back method with spirals of lengths between 0.3 and 11 centimeters long. And we characterize the propagation losses like that. And we achieve at 405 nanometers around 1.5 dB per centimeter. And these were the best. And the ones that we routinely achieve are around 2 dB per centimeter. So it oscillates around that with the best 1.5 at the moment. The cross-section of the waveguide is 700 nanometers thick by 600 nanometers wide, which is the widest that you can have and still be monomode. And we observe that, of course, as you go from narrow waveguides to wider waveguides, the losses reduce, because at the moment we are limited by the sidewall roughness. So we are working on that.
And another thing, we characterize it at 405 nanometers wavelength because at this moment was the laser that we have, and now we have purchased 2 new lasers at 360 nanometers and 280. So we should be characterizing these waveguides at those wavelengths soon. And then we did a collaboration between the Professor Boller's group at the University of Twente, Fix, who did the packaging, Lyonics, which also assist with the packaging, and Toptica. And basically, we designed an external cavity laser where you have here an indium gallium nitride 400 nanometers gain section, but coupled to the external cavity. You can see the Vernier filter, a tunable output coupler, and some phase section. To produce a tunable laser in the near ultraviolet. Here you can see the cross-section of the waveguide. So in this case, it's 100 nanometers thick and 400 nanometers wide. And it's surrounded by SiO2. In the photo on the left, you can see the lasering operation. So basically, we pump, we activate the gain material, and you can see the light entering in resonance in the rings. We got a 0.74 milliwatts of output power in the fiber. So this is what we measure at the end of the fiber. And a tunability around 403 to 408 nanometers, and this is limited by the gain bandwidth of the indium gallium nitride chip that we used, and a side mode suppression ratio of 43 dBs, as you can see here. We also studied the drift, it's a low drift, and the line width is below 25 megahertz. And I say below 25 megahertz because it was really difficult to characterize. So yeah, it was very difficult to do the heterodyne detection, and yeah, it was basically a nightmare. So we can guarantee that it's below 25 megahertz, but we don't know how narrow it is. And you can read more about it in the archive paper that we just uploaded. Now I would like to explain to you operation. I'm going backwards. Sorry. In around 1 micrometer operation. So we can, by co-doping, so during the sputtering process, we can deposit our aluminum oxide layers co-doped with different rare earth ions. And in this case, we have co-doped with ytterbium, so that means that the gain is around 1 micrometer of wavelength. And we use this to do some just simple lasers, like you can see here in the picture on the left, just a ring that you pump, and then you get some laser. And we characterize the line width, and it's around 250 kilohertz line width, and we did that by heterodyne measurement. And we measured 1.6 milliwatt on chip threshold and 2.5% on chip efficiency. So it's not the best laser in the world, but at least we show that we can provide a gain in this wavelength range. And we use these lasers for optical biosensing. You can see the paper here, so it was to do a label-free biosensor. We did a more advanced design because we thought in the single ring we could not control very much the coupling of the pump and the outcoupling of the signal. So we did basically a WDM to couple into the ring, and then we reduced the threshold and we increased a lot the output power. We can also dope with erbium, and now you see that erbium corresponds to the C-band. So I'm going to show a little bit about the performance of our material and our amplifiers in the C-band. So the first thing we need to know are what are the passive losses, because that will determine how much also gain we can get, because if we have very high losses, then it's very difficult to have good gain. So we made some rings with different coupling gaps to try to characterize the propagation losses. So in the graph in the left, you can see the internal Q as a function of wavelength going between 1500 and 1600 nanometers. And you can see that the Q, this is 9 million here, so it's around 4 million up to 8 million. So from that, we extracted the propagation losses in dBs per meter, and they vary across this wavelength range from 1500 to 1600 between 7 and 3 dBs per meter. So we thought, okay, that is good enough, so let's dope the waveguides with erbium. So we did 2 types of devices. In the first one is here in the left, is just erbium doped aluminum oxide chip, and we have erbium everywhere. So then the problem, of course, is that, well, this is, okay, an amplifier, that's fine. But if you want to combine it with other functions on the same chip, you don't want all the functions to be erbium doped. So therefore, we developed an integration strategy where we have the passive waveguides in one layer and the active waveguides in another layer. So the passive waveguides that we use in this project are silicon nitride waveguides, and of course the active is our erbium doped aluminum oxide. And by doing these adiabatic couplers, we can achieve around 0.2 dBs of losses per coupler. And we are working now towards reducing this number. But you can see here a chip that is fabricated using this technology. So yeah, everywhere is passive. And then here is the adiabatic coupler. So then is where it passes from silicon nitride to the aluminum oxide. And then you see the inverted spiral, and then again comes out and goes to the output. So this is the layout of the chips with all the spirals. So we did spirals of different lengths to try to study what kind of gain we were achieving. And this is the cross-section of the mode. So here is the width of the waveguide, and this is the thickness. So you can see that it's around 1.5 to 1.9 micrometer width and around 800 nanometers thick layer. So then we have a good overlap between the pump, which we use 1480 nanometers of pump, and the signal. And in the graph in the right, I show the internal net gain of these amplifiers for erbium concentration of around 410 to the 20 ions per centimeter cubic. And we pump bidirectionally with 130 milliwatts of pump power. So in the graph, you see the internal net gain in dBs as a function of the launched signal power in dBms. So you can see that at 1532 here, you can have very high internal net gain, 30 dBs, and at 1550 is around, say, 13, 14 dBs. And then you can see that it reaches, yeah, you can launch with gain down to -5 dBm, okay? But we wanted to also design amplifiers that you could put bigger signals and you also get higher output signals. So we optimize the cross-section and also the doping concentration. So this is very good if you want to launch small signals, and then you have a lot of amplification. And then if you do a lower erbium concentration, in this case we have 1.510 to the 20 ions per centimeter cubic, we launch a signal of around 7 dBms, and we achieve 27.8 milliwatts of output power. Here you can see we launch this at 1550. So we launch the 7 dBm, and then we see the gain, the total gain achieved, and we can see that it goes up to, yes, close to 8 dBs for a launched pump power, bidirectionally launched, of 200 milliwatts. And then we can achieve this output power. So, yeah, so we are very happy with these results. So, yeah, we will be writing some papers about this in the near future, hopefully, once we have some time. And then the next doping that we are investigating is the thulium, because this is very interesting because the emission is around 2 micrometers. So this can be used for spectroscopy. So then we started a European project, the FemtoChip project, in which we are combining our aluminum oxide doped with thulium with silicon nitride waveguides. And these silicon nitride waveguides in this project are provided by Ligentech. So this is a design of the cavity. So you can see here the gain material is deposited in this section. That's where we provide amplification at 2 micrometers. And then they have designed a saturable absorber, that is this device here. And this is just the launching of the pump and the signal. So what we demonstrated in this device is a passively Q-switch laser. And this is the on-chip output power in milliwatts. So you can see that as you pump it harder, you can reach out up to 200 milliwatts of output power with a slope efficiency of around 40%. And this we have just submitted for publication, so you can see here. It's not yet, of course, accepted, but yeah, it's submitted. Okay, so that reaches the conclusions. So basically, I want to have transmitted a message that the aluminum oxide platform is a very interesting platform for photonic integrated circuits because it can provide low-loss broadband operation from the ultraviolet, around 200, 250 nanometers. We still need to characterize it down there, till the mid-infrared. And by doping it, we can obtain gain at different wavelength ranges. Of course, these peaks are now commercially available via Alluvia, so if anybody is interested, please just contact me. And we are now trying to set up some MPWs because, of course, we're very early stage startup, so we're figuring out how to set up an MPW. But if you're interested in participating in any of the share runs that we're going to be doing during this year, just let me know. We are quite flexible at the moment because, yes, we're basically getting organized. So, thank you very much for your attention.
Thank you very much, Sonia. Very interesting talk. Thank you for the overview of Alluvia. So any question from the audience?
Yeah, thanks for the talk, Sonia. Actually, you replied partially to my question I had in mind because you were showing at the beginning different losses for the different wavelengths.
Mm-hmm.
You show that it's not due to absorption because you show the spectrum, so I guess it's mainly scattering loss.
Mm-hmm. Yeah, and that scales with the wavelength.
Yeah, but you show for lower wavelength, so you have same waveguide dimension for both experiments.
Oh no. So what I don't know now from the top of my head if the overlap with the sidewalls is the same in all the waveguides, but for sure at the 1550 they were like 800 by 1.5. Yeah, no, I can. Yeah, I need to check that. But our conclusion was that it is related to the scattering. It's not about the absorption.
Thank you.
Mm-hmm.
Great talk. About these losses, is this related to the deposition technique, the sputtering? Are you thinking into going for ALD, like your thickness 70 nanometers, it seems a bit thick for ALD, but still within the window. So is this something that you're going to try? And how is the...
Yeah, like the deposition technology, yeah, we like the sputtering because it's more manufacturable, especially when you go to thicker waveguides. Yeah. And also the material that we have developed is very interesting because you can basically anneal it, you can heat it to high temperatures, and it doesn't produce higher scattering as it can happen with the typical ALD aluminum oxide layers that you cannot heat above certain temperature. Mm-hmm. So then that means that we can put a cladding that has low losses, and that enhances our waveguides.
So this scattering, this roughness comes from your lithography limitations, or your reacting ion etching process for your lithography?
Yeah, exactly. So we're working now in improving the lithography, and then the next step is the etching to see if we can somehow smooth further the sidewalls.
All right, cheers.
Mm-hmm.
Hello. Have you developed some device for the mid-infrared?
The highest that we have gone is the devices at 2 micrometers.
Because when you go to the mid-infrared, I think the substrate you don't have you can use silicon oxide anymore. What would you do it? How would you do in that case?
So we are we have not gone there yet, and probably it will take some time until we even think about going there. But yes, you need to. If you use this technology, the aluminum oxide on top of SiO2, you need to remove the SiO2. But we are developing, but this is now in the research group. We are developing another technology, which is the silicon nitride on sapphire, and that should really allow us to go really to the 5.5 micrometers. And we are starting now a funded project where we're going to further develop also that technology.
Thank you.
Any other question? Okay, so thank you very much, Sonia.
Okay. Now it's time for our colleague Victor Torres, and he will present the company Illumina.
Yeah, thank you very much, Gloria, and thank you very much, Pascual, for inviting me here today. It's really a great pleasure. I'm also coming with two hats. I'm professor at Chalmers University of Technology in Sweden. But a bit longer than just a year ago, we spun out from my research group because we had really interesting research results that the industry was actually asking us. So, okay, thank you. So Chalmers is located on the west coast of Sweden, in Gothenburg. It's the second largest city in Sweden. And I belong to the microtechnology and nanoscience department. It's a nice building. I think it's a great pleasure to come there every morning. So I think we're leveraging two things. I think one is the research results that come out from my group, and the other thing is this fantastic national infrastructure for nano and microfabrication. So it's called MIFAB, and includes a network of different clean rooms in Sweden, where the best, it's not because I'm there, but it's truly the best. The best one is Chalmers. The good thing is that this is an open infrastructure where it's meant to host both research groups as well as businesses from small and medium enterprises. Our particular clean room area is more than 1,200 square meters. And we have lots of processing capabilities, which is mostly working for 4-inch wafers, but there's many other groups, many other tools and processes that are meant to operate at 6-inch. And in the context of silicon nitride, I will talk about, we really have state-of-the-art thermal processing tools like LPCVD, E-beam lithography that can operate really nicely on 4-inch wafers, and then several plasma processing tools. So what we're doing is truly capitalizing on more than a decade of excellence in research since I started my group at Chalmers. So at my research group, we work on silicon photonics, mostly on silicon nitride, with applications in the context of kernel linear optics. So we want to harness the kernel linearity to do practical applications in the context of supercontinuum and microcomb generation. Very often we fabricate the devices downstairs, we bring them upstairs at my lab, where we do really nice measurements with laser frequency combs, laser spectroscopy, and often we realize that some commercially available tools are not there for the things that we want to measure. So we develop our own characterization techniques. And then at the end of the day, what we want to do is to utilize those components for practical applications at the systems level, mostly in the context of fiber optic communications, but we're also looking into spectroscopy. And that is also something that we do in collaboration with other research groups at Chalmers, so we just have to move, everything is in-house in the same building. So I'm also going to give a little bit of overview on planar integration and why is that interesting. But I'm gonna come from the angle of nonlinear optics. So what is the rationale here when you compare, for example, to the standard technology, which today is based on a highly nonlinear fiber? So if you want to harness the kernel linearity in a planar integrated waveguide geometry, when compared to a standard highly nonlinear fiber, you have a much higher kernel linear parameter thanks to the fact that you are confining everything to the core dimension of the waveguide. If you do things right, you could have an even higher nonlinearity because ideally you would like to utilize the stronger kernel linear coefficient of your core material. One thing that is also very important is that you can control with lithographic precision both the cross-section and the length of the waveguide. That means that you have exquisite control of the dispersion along the propagation length, which has been a long-standing issue when working with long nonlinear fibers. Typically, they have very high power handling capability, and it has much higher Brillouin power threshold. That means that these waveguides can sustain very high optical continuous wave power without being affected by reflections. The drawback, of course, with planar integrated waveguides is that you have much higher losses. And this means both linear losses, mostly due to scattering losses, nonlinear losses when we use materials that exhibit an optical bandgap that is low. And you also have relatively high coupling losses from both input and output. So there's essentially, when it comes to kernel linear optics in planar integration, there's two schools of thought here. There's one that advocates for using semiconductors, such as, for example, AlGaAs on insulator, semiconductor on insulator, and others. And what they are advocating for is that the kernel linear coefficient can be very, very large, and you also have nice fabrication simplicity and so on. The problem with this material is twofold, is that this type of materials is that they typically have a much higher refractive index, and as a result they are more susceptible to scattering losses, and they also have a lower optical bandgap, and then as a result, if you operate in the near infrared, they typically exhibit also nonlinear losses. And there's the other school of thought where I belong, that advocates for amorphous dielectrics, such as silicon nitride, tantalum pentoxide, and so forth, where you don't have as high nonlinear Kerr coefficient, but because the refractive index is a bit lower, you can tolerate much better the sidewall roughness in your waveguides. So we in particular are focusing on silicon nitride, and we're of course not the only ones in the world. I mean, if you look, for example, for research groups, this approach was pioneered by Michal Lipson in Columbia many years ago. But there's many other groups, EPFL, Chalmers, NIST, UCSB, who are really advocating for stoichiometric silicon nitride. And this is now commercially available, Onyx, Liantech, Gent, Anelo, and others. So in the context of nonlinear optics, this type of material gives you a sweet spot between what you can achieve with semiconductors versus what you can achieve with other dielectric, such as just silica and air interfaces. And at the end of the day, you have a decent Kerr nonlinear parameter, and you can achieve extremely low losses. And here there's also two schools of thought when it comes to achieving ultra low losses in stoichiometric silicon nitride. One is the one that you see on the left, and it consists of having an extremely thin core geometry with a very big buffer of silica, both undercladding and uppercladding. And the idea here is that this core geometry is way more resilient to scattering losses, okay? And in fact, this has been developed for many years by the group of John Bowers at UCSB, and I think it's now commercially available by Anelo Photonics, and they do exhibit extremely low losses in the telecommunications band, below 1 dB per meter. There's true drawbacks with this approach. There's no free lunch. One is that it has limited dispersion engineering capabilities, and that is not good for nonlinear optics. And because the mode is so large, you have a limited bending radius, so this is also not very good for dense photonic integration. So what my group and others are working on is on a different geometry where you are strongly confining the mode inside the core. So that gives you the possibility of more tight, dense integration, and you have the flexibility to engineer your dispersion. So with this approach, the geometric contribution to the overall dispersion of your waveguide is such that it can offset the inherent material dispersion. And this is just ideal for nonlinear optics. And I will show you in a second that thanks to some recent developments, now it is possible to enter into ultra-low loss regime, namely in the order of just a few dB per meter propagation losses. So this is the process that we developed at Chalmers, and it's now transferred to Illumina. So we work on a subtractive manufacturing process. And then here we start with a thermal oxidized wafer, and then we fabricate some trenches by lithography that helps us in controlling the cracks that otherwise happen when you operate with a very thick silicon nitride film. So thanks with this optimization of the crack barriers, now we have pristine areas on the wafers where we can manufacture really nice top quality silicon nitride photonic integrated circuits. So we deposit the silicon nitride layer in 2 steps. That is for controlling much better the thermal cycling of the films. And then afterwards, what we do is patterning the devices on a 4-inch wafer with E-beam lithography. We perform a series of annealing steps that helps us in breaking down NH bonds and bringing down the losses to the few dB per meter range. And then we encapsulate the photonic integrated circuits, and then in some cases, if we want to build some thermo-optic heaters, then we have a lift-off process to deposit some metals. So this is something that took us really a decade to develop, and now we're at the point where we're achieving on wafer about between 2 to 3 dB per meter. And the key aspect of the subtractive manufacturing process is that it's much easier to transfer to a large scale foundry if they want to manufacture this in the millions of components per year if needed. You have a much better control of the aspect ratio of your waveguide across the propagation length. And the key point here to achieve this ultra-low loss was optimizing the etching recipe, optimizing the multipass E-beam lithography, and then we also see in a second that we also have some optimized designs for adiabatic couplers. So one thing that we realized when optimizing our etching recipe, of course, we optimize something in the clean room. We go to the SEM, look how it looks like, and if it's not good, then we come back and we iterate until we're happy. And then we realized that at some point the SEM was not good enough because there were some variations in losses that we could measure in the lab, but we couldn't really see the sidewall roughness in the waveguides. And the reason being that we're right now achieving some sidewall roughness way below 1 nanometer. So that means that we're literally approaching sidewall roughness that is at atomic layer resolution. So what we did is to develop a new OFDR to measure the losses in a non-destructive fashion. That also helped us a lot to improve our designs of beds. And the key point here of this OFDR technique was that we were calibrating the nonlinear tuning of our laser with the aid of a self-reference frequency cone. So in this way, we could measure at each and every time the location of the frequency of the laser with 15 digits of precision, and we could distinguish when measuring the photonic integrated devices what was the systematic error that was coming from the nonlinear tuning, the systematic error that was coming from the dispersion in the system. So in this case, we could manufacture optical, we could manufacture waveguides that were longer than 1 meter, while we were keeping losses in the order of 1.4 dB per meter. So this is one of the best devices that we have fabricated. The mean loss for that wafer run was 1.7 dB per meter. But as I said, we typically can get on a wafer between 2 and 3 dB per meter. That's really the standard. So this 1.4 dB per meter is truly the best, the world record loss that I have seen for the strongest optical field confinement waveguides that are longer than 1 meter. So just looking a bit into what we did. So we had these two aspects that were critical in improving the designs and going beyond the writing field in e-beam lithography. So first thing was to manufacture some photonic integrated components with special bend designs whose curvature was designed to minimize coupling both to the radiation losses and coupling to higher order modes. And the other thing that allows us to very densely integrate photonic integrated circuits within the writing field. But often we had to concatenate a few different waveguides to span beyond the area that was given by the writing field in e-beam. So what we did, we had to compensate for this famous stitching error. But what we realized is that this stitching error is actually something that is deterministic. You can actually measure it, and you can pre-distort accordingly your design. And after active compensation, everything will look as if, once fabricated, as if there was no different writing fields. So that allows us to fabricate these really long spiral waveguides whose area was much longer than just one writing field, but in a really nice and compact manner. So today, what we can offer is ultra-high Q resonators. If I don't get 10 million, I'm not happy. We usually get between 10 and 20 million for this strong confinement geometry. We can offer ultra-low loss optical waveguides. We have controllable coupling, linear coupling between resonators. We have also heaters on top to control the location of the resonances, and we'll see in a second that is quite useful in the context of microcomb generation. We also have low loss interfaces to couple light to lens fibers. We can adapt the cross-section geometry to different to cover different wavelength ranges. Because most of the applications that we're interested in are in the context of telecom, we have adapted and optimized everything to 1.5 micron. But in some other projects, we have worked at 1 micron. So we have also developed an internal parametric script design based on Python that is now being transferred to Lucida. And again, everything is working on a 4-inch wafer processing. So what you see here is the area defined by our trenches, and then inside you can see a pristine area where you can manufacture hundreds of photonic integrated devices with 100% yield. Yeah, so regarding the layout, we have resonator cavities, the bends and the spirals that allow us to have more fancy and sophisticated photonic integrated components. We have standardized our chip design so that if you want and package that with an external foundry, you can do it. And this is how it works. So we design everything depending if you need, for example, nonlinear optics, we can do with our own Python scripts to optimize the supercontinuum or the microcomb or whatever you want. We can optimize the dispersion for that particular fit. We do our layout in Python currently with our internal library. We have the design rule checks, and then everything goes to the beamer, and then we fabricate everything. So depending on how difficult the design is, this whole process may take between 3 to 9 months, and also depending on the availability of the tools at the nanofabrication lab. Yeah, so the cool thing here is that we're not really a foundry. We are more working with customers to fit exactly what is it they need. So we work together on a project, and we customize the designs for them. And we have great flexibility because we're small and because of the e-beam. So we can adapt everything to what the customers need. From 200 to 740 is our standard, but we can go to different thicknesses. And we can achieve extremely low losses. In this case, this is a waveguide that is optimized for nonlinear optics. So we have equivalent losses of 2.7 dB per meter. statistically from many different devices. And then we make the thin waveguide geometry that is optimized for single mode linear optics in the telecom range. We have an order of 4 dB per meter. So unfortunately, I have so many NDAs with the customers, so I cannot really show you practical examples and demonstrators, but what I will do is to show some practical examples and demonstrators that are coming out from my research lab. So one of the interesting applications is in the context of microcom generation. So I will spend just one tutorial slide on microcoms. So the idea is to exploit the extremely high Q that is available in our resonators and harness the intracavity buildup of the intensity, which is proportional to the finesse of the cavity. So if you have a very high Q or a very high finesse, that will translate into an extremely high optical power that is circulating inside the resonator. So what you want to do is to come in with a laser light, a continuous wave laser, and match the mode to one of the longitudinal modes in the cavity so that we start building up the power inside the resonators. And if you do things right, you will harness the kernel linear optics inside the resonator, and you will start to populate the longitudinal modes in the cavity via 4-wave mixing in a way, and you will generate new frequency components that, if you do things right, will be phase locked to the continuous wave laser. In the time domain, that will correspond to a train of short optical pulses that is circulating at a rate that is commensurate to the free spectral range of the cavity. So in other words, you are really generating a frequency com on a chip. The cool thing about this approach versus modular lasers or other chip-scale frequency com generator is that it's a truly parametric process. So the amplification of the vacuum noise is enabled by a parametric amplifier. And that means that the gain bandwidth can only be controlled with the dispersion of the cavity. So if you do things right, you can have a gain bandwidth that is orders of magnitude larger than what you can achieve with just stimulated emission of radiation. The repetition rate is set by the free spectral range of the cavity. And the beauty, as I mentioned before, is that the enhancement of the intracavity is proportional to the finesse. So if you increase the FSR, the whole thing will become more efficient. And this goes in reverse to modular lasers, where you need to have very long optical cavities in order to have sufficient gain. So it's much easier to achieve higher free spectral ranges with this technology. The other thing is that this is an all-optical process. So you just go in, tune your laser, you generate a clean frequency com with a rep rate that is offering a timing jitter that is similar to what you can achieve today with state-of-the-art dielectric resonator oscillators. And the whole thing is in principle potential for integration when you start thinking about combining silicon nitride with your pump lasers and circuitry. And the formation of laser frequency coms come in a couple of flavors. So you can engineer your resonator in a way that it displays anomalous dispersion. So that means that the blue components will travel faster than the red components. And then as a result, the free spectral range will increase with optical frequency. And in that case, you can generate solitons. So very short optical pulses whose envelope will match a second hyperbolic profile. And then if you engineer your optical cavity so that it has a normal dispersion, that means that the blue components will travel slower than the red components. Then what you can achieve are modular dark pulses or dark solitons in these cavities. So these temporal solitons that you achieve in the anomalous dispersion regime are very smooth, very coherent, but they have hitherto the drawback that the power conversion efficiency has been typically very, very low, in the order of just 1%. In the normal dispersion regime, the power conversion efficiency is much higher. So the amount of optical power that you have in your com versus the amount of power that you send in with the CW power is much higher. But it's difficult to access the com states from a continuous wave laser, and the distribution of power is not so even across the spectrum. So one thing that we did is to leverage this high conversion efficiency from these normal dispersion microcoms in some of our devices fabricated at Chalmers. We sent the samples to DTU, that they themselves had a collaboration with Fujikura, that they provided them 37-core optical fiber, and they wanted to use our microcombs as multi-wavelength carriers for both wavelength and space division multiplexing. So here they put everything together. They actually did a truly hero experiment and demonstrated that it was possible with this technology today to light the hundreds of channels that will be needed for space division multiplexing. So in this case, they achieve a record 1.8 petabit per second, and the beauty is that everything is just coming from a single ring resonator, single laser that is lighting everything there. And this is just to show the great efforts by the PhD students there. So for each and every wavelength is just one WDM channel, and that is being measured for each and every core in the fiber. So they automated the system, definitely. And the COM was operative over the full week span of the experiment. This is another practical example that leverages the fact that we can control very nicely the dispersion, that we can manufacture things on a wafer scale. And it's a collaborative project between my group and Andy Weiner's group at Purdue University, that they themselves are in a DARPA project where the aim is to develop optical clocks on chip. So you want to use these microchromes to read out the very fast oscillations from an atomic transition that is coming somewhere in the near infrared or the visible range. And the challenge here is to use these microcombs, because what you want to do is to read out the oscillations with electronics. And what you see here is a comb that is designed at my team and fabricated at Chalmers, that whose bandwidth spans an octave. So what we do here is to have yet another comb that helps reading out the terahertz rate. So this is beyond what you can do today with standard electronics, but with the aid of these two combs that are offset in line spacing, we can down convert and measure the rep rate with standard electronics. Furthermore, the other thing that is here very interesting is the capability to measure and read out the carrier envelope offset frequency. So the comb has 2 degrees of freedom, that is the pitch and the offset. So we can read both with standard electronics. And after reading them, we can act on the microcomb system and stabilize the whole thing. And what you see here is the carrier envelope offset frequency stabilized to an RF synthesizer, and it's averaging down to the limit given essentially by both the RF synthesizer and our measurement or their measurement capabilities. So the other thing that we were working in my team is towards overcoming these fundamental issues in the formation of microcombs. So we're starting to explore with these 2 linear coupled cavity arrangement. And we like to call them photonic molecules if you think of a single microresonator as an artificial atom, where the role of the discrete energy levels is being played by the longitudinal mode resonators. So you could think of having these 2 individual resonators with their corresponding family modes of longitudinal frequencies, and it may be that one of these frequencies is degenerate. Okay, so that means that the same color will be resonant in both cavities. So nothing will happen if you have these two resonators completely isolated, but when you bring them together, they are linearly coupled, and what you observe is that that longitudinal mode is going to be a split. It's similar to what happens in the binding of the diatomic atoms to form molecules. The beauty here is that you can control in a very reliable manner the split, and that turns out that results into fascinating new physics that can be not only cool but can also be exploited for practical applications. So one thing that we did is to push that optical frequency to compensate for the inherent frequency mismatch when you generate the soliton in the single microresonator. So this is a beautiful parabola, and what you see is an outlier, but that's exactly where we want it to be. And in that case, we can compensate for that inherent mismatch. And what we are observing is now we're overcoming this fundamental issue in nonlinear conversion efficiency of solid-off microcombs. And we can generate outstanding power conversion efficiency in a very compact fashion and in a process that is manufactured at the wafer level. So we have patented the design, and we have transferred the IP also to Lumina. So we think in the future that this could be a very nice opportunity to capitalize and develop further products. So we have packed the device. We observe outstanding stability and also drifts in an hour that in a day that are just less than 1 megahertz. So just to summarize, so this is just a new startup that we are developing organically. No investors. Is truly being responded by demands of customers and industry. So what we offer is design and prototyping services that can capitalize of the extremely high quality and the ultra low loss silicon nitride process that we have. We offer great design and flexibility, short turnaround, and very high performance. So that's all. Just thank you very much for your attention.
Thank you, Victor. Any question in the audience?
Thanks, Victor. Nice presentation. I have a question. Actually, you have a picture there, and you mentioned quickly. The question is about your trenching, your initial process of trenching, I guess, for stress release for thick nitride. How does this affect to the useful area of your wafer? Because you commented that this trench is an external square, but is it in the design area? Do you need that as well or not?
No, it's only in the outer side of the wafer.
And how that would affect to your useful area?
You cannot write here, but that's because the design is square, but you could make it rounded. And we have seen that this also works on 6-inch wafers, so it can work on larger wafers. But just to be clear, you don't have to manufacture anything inside that area.
Thank you, Victor. Very impressive talk. I have a couple of questions. One is about what's the sensitivity of these comms to temperature. And the other one is about practical applications of these comms in power applications. One challenge, as far as I understand, is once you have generated this ultra-wideband comm, how to amplify it for applications where you need, let's say, watt level average powers.
Yeah. So the first question is about the temperature. So it follows the thermo-optic. So there's two aspects that can modify when you increase the temperature, and that is the change in refractive index, so the thermo-optic coefficient, and the other one is the thermo-expansion coefficient. So the thermo-optic coefficient is the one that is larger, and that is the one that dominates. I don't remember from top of my head, but it's what we see in the lab follows standard values published in the literature for silicon nitride. I just don't remember from the top of my head how much it drifts per temperature, but it's definitely lower than silicon. And the other part of the question is about how does that affect the microcoms. So you need to enable a lock-in between the CW power and the microresonator, but that is really not a problem. I think for two reasons. There is an inherent thermal locking mechanism in these microcoms. So actually what happens there is that the resonance follows the drift of the laser. So what you need to do is to ensure that can maintain over long term. So you can measure the power and then either feed back into the ring or feed back into the laser. So that is essentially what we do in the lab, and it works pretty well. So the other question with regards to the practical applications, it does depend on exactly how much power you need. I think for some applications where you may need just 1 milliwatt or so per line power, I don't think that you will need an amplifier there. I think with these new designs that are extremely power efficient, if you come in with maybe, let's say, 100 milliwatts of pump power, yeah, I think you can get there. If you need way more than 1 watt, then you will have to interface with an external optical amplifier that can get you there, and then of course you will have to redesign your cone within the gain bandwidth of your amplifier. But for some practical applications, I think you will not need optical amplifier thanks to this new design of power efficient microcoms.
Okay, thank you. One more question here.
Hi Victor, thank you for the very nice presentation. One question about the very low loss achievement. Is the E-beam a key ingredient, or can this technique also be translated to other lithography?
Yeah, this is a speculation, of course, because we only work with E-beam. But I don't think that it will be needed, because the writing features that we get there, you can achieve them with a stepper, I think.
Okay, thank you.
Okay, so let's start. Let's go ahead with the last speaker. Thank you very much.
So last but not least, we have with us Daniel Segura from MAPSI Photonics. Thank
you. So hello everybody, I'm Dani, I'm the CTO of MAPSI Photonics. First of all, I would like to thank Pascual for giving us the opportunity to participate in this conference. It's always a pleasure to come back to where you studied. So let me explain a bit more. What is MAPSI Photonics? MAPSI Photonics, we are a company. We are a company that manufactures infrared filters. We don't work with integrated photonics. We work with free space photonics. In our case, the idea is that we integrated our filters. We manufacture filters that some of our clients integrate in more complex systems. And these systems are mainly thermal cameras and gas sensors. We work specifically in the mid-infrared and long-infrared regions, above 3.5 microns. The idea is that our filters are a plug-and-play product. That means that we are entering in a market that is already created. Therefore, we don't need to create this market, and these applications are already there. So what we will create is an incremental, at the beginning of the stages of our company, is create an incremental improvement of whatever is already in the industry. What are these mainstream applications? Mainly it's industrial monitoring, gas leak detection, and thermography. Our filters allow us to select what does a thermal camera see. We can select these temperatures that we want to see, and also we can select which gases we want to see. It's an spectroscopy in the mid-infrared and long-infrared. As you can see, these applications, these products that are already in the market are experiencing a really high growth, mainly thanks to the Industry 4.0, because they are trying to monitor every stage of the industry. And that's where our filters enter into the market. Let's see some of the problems that these products have, and that they are mainly related, they are somehow related with the conventional filters that our competitors can manufacture. First, they have a low reliability of the measurements. They have also they are limited to standard applications, and there is also another one that is limited user experience. And why do they have these limits? This is because they use filters that are very expensive and they have a low resolution. Especially if you go towards higher wavelengths, they are more difficult to fabricate and more expensive to fabricate. Also, low robustness to ambient variations and high maintenance. It's something that well, we will see later in this slide. This is a current multi-layer filter. How are they manufactured? They are basically a combination of high refractive index with low refractive index materials located on the top of a transparent material in the wavelength that you are interested in. Which problems do we see there? They have low optical resolution. I'm talking especially at long wavelengths. Why? Because if you go to higher wavelengths, you need thicker layers. Every time you want to increase the wavelength, you have to go towards thicker layers. And that means having more problems in adhesion, having more problem in stress, having more problems with humidity, and that has an impact in the final product. And this impact is that they have low optical resolution. Also, something related to that is that there is an environmental dependence. The filters absorb water and they degrade really easily. After, if you put them in a very hot environment or a very humid environment, they can really easily degrade. Also, there is a point that the market demands. There are a lot of specific clients that don't want to produce 50, 100 filters every time. It's a market that it's very commonly focused on ad hoc products. And these filters are manufactured in sputtering magnetrons or E-beam magnetrons, and that means that you fill a chamber with 100, 150 filters, and you always get these filters. And that means that you are getting a huge stock, or that the development of one filter is very, very expensive. And another aspect is that the production of these filters and also the material used, sometimes they have a huge impact in the environment. And what's the solution that we propose? The idea is doing something similar, but instead of depositing one layer on the top of the other one, we are taking advantage of the silicon photonics. The idea is that we only use one material, but we modulate this material. We grow pores, or we etch pores in silicon, and we create modulated structures. That means low radius and high radius, and that translates into low refractive index and high refractive index. We create this analogy with multi-layer filters with three-dimensional filters that are the ones that we are manufacturing. Indeed, they are three-dimensional photonic crystals. That is a layerless technology, all silicon. We don't have, and this allows us to create really high-resolution filters in the mid-infrared and long-infrared. We also, silicon is very resistant to harsh environment. We can stand for temperatures up to 600, 700 degrees, and we don't see the effect of the humidity in our filters. So that makes our filters especially interesting for harsh applications or harsh environments. Also, we can produce from 1 by 1 to 10 by 10. That means we can adapt to the needs of the clients. And also the development of new products or new filters is something that is less expensive than having to build or to make different runs to get one single design. Also, our production is cleaner because we need very low energy, and also the emissions of CO2 are very low. And this is how filters look like. Imagine you are a photon. I don't know. I don't have the, but no worries. Imagine you are a photon and you are entering in the filter. Ah, okay. Sorry. Yeah, sorry. You are entering in that way. In perpendicular, what you see is this mesh. It's a mesh of holes that, if we cut them and we see the cross section, we go that way. And that's an analogy of a fabric perrot. Basically, we get a mirror here with high refractive index, low refractive index, with this shape. We create a spacer between them, and we create another mirror. What happens there? Fabric perrot. We have a the ray starts to build up inside of the spacer, which is confined between two mirrors, and in that way we can select these wavelengths that we are interested in. By tuning the spacer and by tuning the mirrors, we can go to other wavelengths. So we just need one lithography pattern, and we can go from 3.5 to 10 microns, and we can go even higher without any problem because we only need to change slightly the first lithography. That permits also to avoid the problems of design, because when you have to design a multi-layer filter, you have to design the materials, the addition problems, the humidity that it will be exposed. In our case, we just design a voltage current profile that is applied to our equipment, which is built by ourselves, and this voltage current just lead to the filter that we are interested in, and we don't need to be aware of all these other aspects. I won't enter in detail on the comparison with the other competitors. I just wanted to highlight that when you go to multi-layer filters, the thicker you get to go to longer wavelengths, you have to make thicker layers. In our case, we have the other problem. Our challenge is to go below these features. We have to go below 700 nanometers if we want to go below 3.5 microns in the infrared spectra. So we are stronger when they are weaker. And on the other side, if we put this graph and we take into account the mid-infrared, near-infrared, it will be the other side. We won't be in that position. Also, we want to highlight that there is no any other manufacturer of mid-infrared and long-infrared filters in the European Union. Typical application. Where are we more versatile? We can produce thinner filters. We work with 300 microns silicon wafer, and that permits our clients to be very flexible. We have seen that it's very important for the clients, especially, and we are in the Photonics Integration Week, they are trying to integrate also these filters inside of their devices. So being able to cut these filters to be really thin allows them to make more compact and integrate even more the products, the filters that they are already using currently. As I mentioned, better resolution and also save money because we can adapt the production to the needs of the market. But I will also highlight something that is a bit more disruptive. Our filters are open. That means that they can be filled with some things. They can be used for biodetection, for example. If we fill them with some antibodies or whatever, we can have the measurements, but not with shift in the refractive index, but with absorption of the molecule. That means targeting very specifically what are we measuring. We don't need, we are not so constrained about the labeling or the biomolecules that we need to attach to be selective in our sensors. And also that we have the light confined in a space. The light is resonating in an open space. That means that the interaction is also happening in there. We are not only passing the light one time, but we are confining the light. That means that we are increasing the interaction of light and matter in the infrared. And that's a platform that could be interesting for these applications, also for green energy production and nanoplastic detection. That are some of the products that we are offering. We are working mainly with the clients, ad hoc production with the clients, with the narrow bandpass filters. And we are really happy because this first semester we will be launching a mass production of the neutral density filter. That means having a standard production that the clients can buy without we having to design the filters specifically for them. We can also produce other filters such as notch filters or low-high passband, or we can adapt to the client's needs. Where is the market or what are the requirements of the market that are leading the new developments in filters and that we think that we can really follow? First is having tunable neutral density filters. Tunable neutral density filters are some filters that are put in front of thermal cameras and prevent the saturation of the detectors when they go to high temperatures. That means that you buy the camera, the client buys a filter, puts the filter in front of the camera, and that creates problems with the practical problems, like the filter is dirty, that they degrade really easily, but also that there is one filter from one temperature. We are working towards creating neutral density filters variable. That means that the transmission can be controlled by the manufacturer of the camera. It doesn't go in front of the camera, but it will go inside of the camera. And that allows the client, the user, to select which are the temperatures that they want to see. Another thing is like integrations, as I mentioned before. The filters can be integrated with emitters and detectors. And it's really interesting because having, for example, integrated emitters that allows you to emit thermally just one wavelength or one as narrow set of wavelengths will really make the compact, the gas detectors or the other detectors that use spectroscopy really compact. And that's something that there is a really high demand on the market. Also, mosaic filters. The camera, if you put a filter nowadays, you just see one gas. You see CO2, you see methane, but you don't see all of them. The industry is also pushing to have filters integrated in the detectors and very small filters integrated in the detectors, so you can select, with the camera, you can select which gases you want to see. And that's something that we also think that it will be really important in few years. And also, as I mentioned before, filters for biodetection. Which challenge are we facing? As I mentioned, moving from ad hoc filtering solution to mass productions, at least in some part of our company. Also, increased blocking. We are currently in an OD2. That means we can block up to 1% of the transmission. We want to go to OD3 or OD4 because there are some applications that require this level of blocking. Also, scaling the production. In integrated photonics, there are a lot of groups that are working on new developments, and you can see a lot of people developing new tools. In our case, there's no one doing that. So we need to create all the models, all the physical models, all the programs that allows us to simulate, to fabricate. Scaling the production is something that we have already developed very good tools, software and fabrication tools, and we can produce more or less now up to 5,000 filters a year, which is a turnover of around 1.5 million euros. But the idea is that we have to grow and give more space to standard and mass production. And also, we fabricate inside these pores, but there's a pre-pattern, which I showed you before, this mesh, that we have to externalize. And also, sometimes, depending on the requirements of the clients we need some post-processing. And integrating this post-processing or bringing this process close to our production center is something important because it allows to a reduction of cost, but also a control of the quality and also a reduction of delivery times. It's very common that if you ask for a new filter, a company will tell you that the delivery time will be higher than 12 months. If we can go much below these times, it will be really interesting for us for these niche applications. The company was created after 2 PhDs of David, who is the CEO, and the CTO. They are advisors of MAPSI Photonics. Some of them are part of MAPSI Photonics. And currently we are 4, but next week another girl will join the team. So we are happy for that. And the idea is that we will keep growing because we just received a Neotech, and we are also working on different projects that are giving us these opportunities to grow and to create a technological company with production inside of it. So thank you very much for your attention and for your time.
Thank you very much, Dani. Any question?
Thank you for your talk and congratulations for what you have achieved. I wanted to know what is the size, the area you have for your filters, and also about the repetitivity and accuracy that you have for the response you are looking for.
Yeah, usually we work with 1-inch filters, and the repetitivity is is good, but it's something that we are working on. Usually we get around 10, 50 nanometers Swift, but the point is also that since we can control, first, there is this design that is really quick and easily controllable, so you can fabricate more than one if there is a problem, and we don't have to throw 100 filters if there is an error in the design. But usually there is no a problem of repetitivity. The main problem is to make this 1 inch bigger. Every time that you want to go bigger, you have to really think well how all the circuits that you are creating to generate these pores work. So my reply would be, there's no problem of repetitivity, but there's a problem in growing this area, or something that is more a challenge.
I think the way you fabricate the pores is by vertical process, right?
Mm-hmm.
Okay, I think this can be a problem when you try to integrate such a structure in a photonic circuit. Could you fabricate the pores horizontally, for instance? I think this would enable to. It would be a big advantage.
Okay. Our goal is not to integrate anything. So the idea is that the integration has to be in the emission detection part. And this emission can be integrated because it's thermal emission, and it can be made in one of the parts of one of the sides of the wafer. It's not because we want to put it in a photonic integrated circuit. That's the first. We are focused in industrial application with free space. But regarding the other question, there are some possibilities to create. Indeed, we have collaborated, not we, but David, the CEO, has collaborated with some research centers to do this in integrated waveguides because they wanted basically for biodetection, because they wanted to have inside of your waveguide like holes, small holes to have biodetection in there. It's not a so straightforward process, and this is macroporous silicon. That it's micro or mesoporous silicon. Is a technique slightly different, but well, that can be somehow and in some specific conditions made.
Thank you.
You're welcome.
Okay, if there are no more questions from the audience, I would like to ask you for last applause to our speaker and thank all the speakers of the session. And now I will give floor to Pascual for the closing set.
Okay, well, little else to say, just to thank you all for your contribution to the event 1 year more. Thanks to all invited speakers, sponsors, exhibitors, all becoming like a small friends and family ecosystem on photonic integration around Spain, and with the contribution from other companies and participants from the rest of the world, I must say. So thank you very much, enjoy the lunch, and hope to see you next year.